In this chapter, we will be discussing neural networks. In the previous chapters, we have extensively discussed the linear models for regression and classification. Both of these models are based on a linear model where the weights are the function y is a linear function with respect to the weights, where the weights are a linear combination we constitute a linear combination of weights, weighted in fact by basis functions of our input vectors. And for the case of regression, we would have a function f which is an identity. So basically this argument here, the sum of all linear combinations of weights and basis functions, will be the outcome for our regression. In case of classification, we will additionally have this function f, which will be a nonlinear function generally, which will be typically we use sigmoid or softmax, but there could be other functions as well. And this function will serve that it maps the entire range of the real axis from minus infinity to plus infinity to the range of 0 to 1 to express the probabilities of membership or assignment of an input point to a certain class. In case of feed-forward networks, which we'll be discussing in this chapter, we extend the concept of the basis functions phi j to be actually learnable, to depend on learnable parameters. And this was the major limitation of our linear models, where the basis functions were in fact not learnable. They were fixed, like for example, polynomial basis functions would be having fixed polynomial formulas, or the Gaussian basis functions would have defined the mean and the variance already, and these parameters would not be learnable. So in case of neural networks, we will actually learn these nonlinear basis functions phi j. And for the neural networks, the way how we learn them is very particular, because the basis functions phi j will be itself a nonlinear function of a linear combination of inputs with the adjustable parameters w, which will be the weights and biases. So in fact, the nonlinear basis functions phi j will be having exactly the same structure as our linear models, and by that we will create two such layers of linear models, one for the basis functions and another one for the outcome of this linear model or nonlinear activation function. So they will be nested, and we will see it in a moment. Therefore, we can say that the neural network model consists of series of functional transformations. We will first start with some activations. An activation will be simply a linear combination of input vectors with the weights in the first layer, that's why we denote here the superscript 1, added with a bias term which serves as an offset, and this will be one activation. And we can have many activations, in fact. So here in this case, we would have the inputs, and we can have many activations. In fact, then we can take this activation and put it as an argument to an activation function h to generate the, uh, the, the value z, and this value z is now in fact like the value which would be outcome of our nonlinear basis function phi jx. So this is now our value set, which itself is an argument in a linear model which is weighted with another set of weights and biases in the second layer. That's why we have here the number 2, and that will generate a new activation, and this new activation will then be again an argument to an activation function, which could be either sigmoidal, tan h, or any other which is meaningful and transforms our real axis into the interval of 0 to 1. So, and we can talk about the outcome from the first layer. That is, in fact, we don't see it. We see the input and we see the output, and in the middle there are also some intermediate values in outcomes of this first linear model, and we call it a so-called hidden layer. So we have a outcome of this, and the nonlinear activation function is a hidden layer z. We can see the hidden layer z here in this schematic drawing. So imagine that we have our input vector, which consists of dx values, which could be scalar values in this case, and they are depicted by these nodes in this kind of a zeroth layer because it's an input. And then we have the hidden layer, and in each of these, so we will have m hidden layers, so we will have one hidden layer which consists of m units, and like for example the unit C1 will be performing a linear combination of all of these input points x weighted by the weights w and plus the bias here. So this is the x0, which will be forming us which will be 1, which will be weighted with the bias term w0 for the first layer. So here these edges are expressing the different weights, and please note that x1 is having one weight for the hidden unit C1, would have another weight for the Z2, another weight for the Z3, and so on. So for each of these hidden units in this hidden layer, the weight contribution from a point x1 will be different. And so it will be for the input point x2 and in fact for all the points xt. So we can see how this hidden layer is constructed, and we can think of it as the nonlinear basis function, and as if we would be transforming these points with the nonlinear basis functions, which is itself a linear model, and then after the nonlinear basis function is calculated, we perform exactly the same linear model as before, where we are weighting the outcome of this basis function, and then individually of each basis function in order to calculate different values for the outputs y. So we can see that here in this case of this network, we would have the input vector x and hidden layer or hidden units, in one hidden layer, and then k outputs in the last layer, which is an outcome. And in fact, this can be also extended for not having only one hidden layer, but we could imagine having several hidden layers and forming a feed-forward network where the information always flows from the left to right in terms of the calculation. So there is no loop or anything which would bring this calculation back to the previous layers. And we could have several of such hidden layers consisting of hidden units stacked before we finally reach the output. And that's why such a architecture is given its name neural network. This term is, is indicating that such an architecture resembles the architecture of the biological neurons of animals and humans, but this is a very loose abstraction from the actual biological architecture of neurons. So this is the origin of its name, but for the sake of this lecture, we will not be making any claims about the biological neurons, only of these artificial neurons and the so-called artificial neural networks. So after we understand the neural network architecture, let's have a look at how this is represented in an algebraic form. So we ended up on the previous slide with having the AK calculated, and for regression, that would be the outcome. So we will have the YK will be equal to the AK. For classification, we will still be using some nonlinear function in order to transform the AK real axis value or real value on the entire real axis into the range of 0 to 1. And that is what is the sigmoid function used for in terms of two-class classification, where we can see the formula of the sigmoid written here, as we are already quite familiar with it. For multi-class classification, we will be using the softmax function. So let's have a look at our structure. So here we would have we are now putting the entire formula for our basis function as we stay with that concept, which is a linear model and as an argument or input to a nonlinear function h forming the hidden layer, and this hidden layer is further weighted with another set of weights for each output, and then where we add a separate bias term for each output, and this is then as an argument going into the sigmoid function, which gives us then the particular value y, which in case of classification will be representing the probability of x being the member of a certain class. So, however, as we often have seen before, that the biases are kind of treated separately, which is algebraically maybe not very convenient, and therefore we can extend these iterators from starting from 1 to be starting from 0, and therefore we can set the value x0 to be 1 and then multiply that with the weight or with the bias term w0 and have a simpler formulation which doesn't have an explicit added bias term, but it's part of the overall sum. And this is known as the neural network architecture known as the multi-layer perceptron, which is a fully connected neural network, meaning that every input is connected, has some non-zero weight with the, or in principle has some weight with the form associated with every hidden unit, and then every hidden unit is contributing through the weights to the outputs. So the weights are connected. There is no absence of a connectivity and between the layers. Only in principle between the consecutive layers. So there is in the multi-layer perceptron is the connection between the first and the hidden layer, or the input and the hidden layer, and then between the hidden layer and the output. There is no direct connection between the input and the output in the multi-layer perceptron. Now, so we have here a simpler formulation where we do not have these weights or biases, sorry, expressed separately, but they are part of our linear combination. We can see that in the nested form, we have first the first layer, the hidden layer here, with the superscript 1, and here is the second layer of weights with the superscript 2, and each time we see here a activation function, either H or sigmoid function, forming us this multi-layer perceptron structure algebraically. It needs to be stated that the term multi-layer perceptron is actually quite a wrong term, because we have already learned in the classification about the perceptron algorithm. And you might remember that that perceptron algorithm was having a special a nonlinear activation and function, and that one was not a smooth one, but was a step function. We might also remember that this step function was categorizing the outcome of this nonlinear function to be either -1 or +1. So there are two differences or several differences from what we have in architecture of the feed-forward neural networks, or MLP, the multi-layer perceptron, as compared to the perceptron algorithm itself. And one is that we are still dealing here with a probabilistic model in case of the neural networks, and we are having a activation function which is smooth and continuous, and therefore differentiable, which will turn out to be very important. And also this function is mapping the real axis to smoothly on an entire interval 0 to 1, while the multi-layer perceptron is mapping the values only either to -1 or 1. So there are several notable conceptual differences which make this term MLP inconsistent with the previously introduced perceptron algorithm. But however, this is in community so ingrained that we will be referring to this fully connected neural network as an MLP, multi-layer perceptron. There could be several extensions of in the neural network, and which would be changing the architecture slightly. One thing is important to mention, that if the activation function of the hidden layer is linear, then the network with a hidden layer can be represented as the without that hidden layer, in fact, because we will simply have a linear combination of weights, and then activation function will be linear, so the model is linear, and it will come as an input to the another linear transformation. So there will be consecutive linear transformations, and this, for example, from graphics, we can see that linear transformations, set of linear transformations, can be represented as a single combined linear transformation. So therefore, if the activation function is linear, then the network with hidden layer can be replaced with a weights which will be actually representing that hidden layer, and the hidden layer will no longer be existing. So in fact, if we will have activation function of a network of 100 so activation functions which are linear for 100 hidden layers, even these 100 hidden layers can be then represented as network without these hidden layers, because all the linear transformations could be then combined into a single linear transformation. Therefore, the activation functions, if they are nonlinear, that would lead to the fact that this network is then not collapsible in terms of the hidden layers, and the hidden layers would be not representable by a collapsed form. Then, so we can extend the concept of the feed-forward neural networks from a two-layer network to multiple layers. So we will have multiple hidden layers where always a linear combination of weights and the previous input from the previous layer will be then as an argument to an activation function, nonlinear activation function in general, and that will form as an output of this layer and forming an input to the next hidden layer. Also, another generalization is the so-called skip layer and the connection, which allows to skip one layer and connect a layer two layers which are not consecutive to each other. So sometimes we even want to have the skipped connector directly between the input vector and the target output. And that will be called the so-called skip layer connection. It will always be associated with some learnable parameter, with a weight which defines how much is the input contributing to the through the skip layer to the desired layer, which is not contiguous with its own layer. And then MLP is defined as fully connected. However, in our network architectures, we can have a certain sparsity. So we do not really, not all neural networks will be fully connected, and some neural networks will have only few connections, as we will see on the convolutional neural networks, for example, later. Always, we will have a certain hidden layer structure where we will have our weights and the previous layers output to be formed a linear combination or a dot product, if you like. So this is summed up. It's a multiply and sum, which is an argument to our activation function, and that forms the outcome of this hidden layer. So we can see here on this schematic diagram a neural network where we can see that this neural network would have like 1, 2 hidden layers in principle, but we see that in the first layer we have only one hidden unit, Z1. In the second layer we have 2 hidden units, Z2 and Z3, and except that these 2 inputs are connected both to the Z1, they are also through skip connectors connected to the second hidden layer directly. So there is an indirect connection both through this hidden unit, and also a direct connection. So each of these edges would represent, in fact, a weight. How much is this input weighted in the sum of the for forming the output value. So we can see that there is one skip connector here. For the X1, there is another skip connector here also, but also we can see that the X1 is directly connected to one of the outputs through, again, some weight. So this shows that the feed-forward networks can have various topology of connectivity, but one is remaining unchanged, and that is that we have our computation is always proceeding from left to right in this diagrammatic form, and we never have like a calculation which feeds back into the previous layers and changes the previous layers values. So one important aspect is that feed-forward networks can be regarded as the so-called universal approximators. This is a fundamental fact which is telling us that in case we have a very like long enough two-layer neural network with a long enough hidden layer, then we can with that approximate any continuous function defined on a compact input domain. So that means that we can approximate any function, and that's why the feed-forward networks are called universal approximators. So we can already recognize that already two-layer neural network has the expressive capability of represent any function. So let's have a look at that a little bit, what that means. We have here an function sampled by the, which is x powered by 2, sampled by multiple samples which are depicted by these blue dots here. And we have here so all these little dots would form an input layer of x, and so on the x-axis, of course, they're uniformly distributed, and they will, as an outcome of this network, we will have the values y as a regression example. And here we can see three dashed lines, green one, then the purple one, and the greenish yellowish one. And these are, in fact, the activation functions, or actually the hidden layer outcomes of three hidden units. So this is one unit, the green one, this is another unit, and this is another unit. So imagine that we have an architecture that has, I don't know how many, this looks like, let's say, 30 input points, and then we have three hidden units. All of them are connected with these input points with different weights, only three hidden layers, and that will serve as an outcome of a number of different y's, where the y is equal to, the number of y's is equal to the number of x's. So, and already now we can see the red line here is the level of how this function, input function, has been, which has been sampled by the values x, has been approximated well. So that we have very well trained with our MLP with three hidden units this quadratic function. And as we said, it is a universal approximator. Therefore, any function can be represented like that. And we have see here another example where we have trained another function, namely the sine function. And here are the depiction of the functions associated with the hidden units. Similarly, we can see here an absolute value function. So it's like y equals x in absolute values. And we can see that this function is also represented by its samples, and the red um, uh, connected curve here depicts how well it is approximated, this function. We can see that here there is where we have a discontinuity in the first order derivative in the absolute value. We have a certain smoothness, so the universal approximator is smoothing this out. Even such an function like this so-called Heaviside step function, which is minus 1 before so for x smaller than 0 and plus 1 for x bigger than 0, or maybe it's 0, not minus 1, but 0 and 1. This can be also approximated just by 3 hidden units, and we can see that the red line, we cannot see it very clearly here, but in this step we see that it actually approximates this function very well. Also, we can see how the neural networks performs not only in the regression, which was this case, but also in the classification. In this case, we have this, you can see these two different classes of circles and crosses, and these circles and crosses are actually mixed, so there is no clear distinction. However, from the input as this input was synthetically generated, this green line here depicts an ideal decision boundary between these two classes. And we have two hidden units, and we can see their decision boundary with these dashes, one decision boundary, another decision boundary, and they together form this red decision boundary, separating the 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 circles from the crosses quite well. It needs to be said that this universal approximation property of feed-forward neural networks is only secured if the nonlinear activation function is not a polynomial function. So it should not be a smooth continuous function, but not polynomial. For polynomial functions, this universal approximation property does not hold. Let's have a look at the how redundant, in some sense, or how similar networks can act in the same way. So, if we have a neural network, we can easily find an equivalent neural network which will have exactly the same property, exactly the same outcomes given the inputs. And that we can observe it by observing the architecture of the individual building elements of networks. So, and we would call this the so-called weight space symmetries, because we have different weights in the weight space where these weights are forming points in this high dimensional weight space, and there will be the same outcome of a neural network. So in terms of from the viewpoint of input and output mappings, but they will have corresponding to different points in the weight space. So imagine that if we change the sign of all weights and biases, and also of the corresponding activation function, we would have we have totally changed the weights, but we will have the same outcome of a certain, let's say, hidden unit. All the weights are negative, so we are summing up all the linear combinations in the same way, but we are reaching a negative number, and then which we can see that, let's say, we will have then, instead of A, we will have a minus A activation if we just turn the sides of all weights, And then we know that, for example, 10H minus A is equal to minus 10HA. So, so therefore, in this case, we will see that if we also change the sign of the activation function, for changed sign weights and the changed activation function sign, we will have the same outcome. So we see here a symmetry that even we have changed for one hidden unit all the signs, and the outcome of the network is exactly the same. In fact, we can say that one weight vector is equivalent to 2 powered by m sign flip weight vectors in this two-layer neural network with one hidden layer. When we have m hidden units, we will have a one weight vector is equivalent to 2 powered by m different sign flip weight vectors, because we do not change only the, say, sign flip of a single hidden unit, but of another hidden unit. Actually, we can change the sign of we can perform the sign flip of all hidden units, and including then the activation function, and the result will be the same, because the sign will cancel each other out when the activation function has a different sign. Therefore, this is forming a weight space symmetry where one weight vector corresponds to 2 powered by m different weight vectors with the same network outcome. Furthermore, we have another aspect where we exchange weights and biases of one hidden unit with another hidden unit. So we simply have the like one hidden unit, let's say Z1 has corresponding to a certain weights and biases, and we simply change it with the Z2 and exchange those two. So in fact, they are the network in itself is different, but and in the end, it will sum in the outcome in the same way, and therefore we will have again another kind of symmetry. So even if we correspond that all weights and biases will have a unique value, we will have this symmetry. And in this case of exchanging the hidden units weights, we can talk about a m factorial equivalent weight vectors. So in total, even for unique weights across all, if all weights will be somehow different and unique, we will still have a weight space symmetry vector 2 powered by m times m factorial, coming from these two aspects. One is the changing signs, and then the other one for exchanging weights between the different hidden units. Of course, there could be more symmetry even in case the weights will turn out to be the same in certain cases, and that will then form additional symmetries which are not regarded in this already a large number of symmetries. After we have discussed the basic structure of neural networks of the multilayer perceptron and its various characteristics and further generalizations into skip connectors and multiple layers and so on, we will turn our discussion to the network training. Before that, we will see the neural network in the context of the two tasks of regression and classification, as we are used to from the case of linear models, but we will slightly change it for the context of the neural networks. And Similarly to the network training, we have also the training in the linear models in the way that we have both a training set again, where we have the set of input vectors and the xn, and coupled with the target observations tn. And we have n, capital N, of these type of observations. Now, out of this, we can, for example, derive for the case of regression an error term with respect to weights, which is 1/2 of the sum of the squared differences. So here we can observe we have a difference between the prediction and the observation, the true value. This distance or this vector is squared, so it's a squared distance, and we are summing it up, sum of square differences. Now, we have had this before, and we know how this came to place. We will just now discuss it, how the regression is then formulated in the case of neural networks. So in the case of regression problem, we will have, imagine, two layers of the neural network, so one hidden layer and one output layer. In the hidden layer, we will have a regular activation and then a nonlinear activation function. And in the output layer, we will have an activation, and the activation function will become the identity, so that we will keep the result of the activation to be in the real axis, so from -infinity to +infinity. From the already chapter 1, in the case of the polynomial curve estimation, we have formulated that the conditional probability of t given a certain position, input position x, and given a certain weights and a certain precision of the noise, or which is a reciprocal of the variance of the noise, is given by the normal distribution of t governed by the mean, which is the predicted value of the y of given at the position x given the weight vector, and the beta inverse, which is the variance. And this is just for one t and a prediction given at a particular position of x. And for all the t's from the training set, coupled with all the x's from the input vectors from the training set, we can express the conditional probability as the product of these individual probabilities from the training set, as they are these samples are independently drawn. Therefore, this is a product of the Gaussian, where each Gaussian is governed by the mean at the particular location y, and then the variance, which is equal, which is the same for all of the training data, and we are multiplying so the probability of this Tn is given by this normal distribution, and we are multiplying all these normal distribution probabilities to get the conditional probability of the entire training set, given a certain weight vector W. We want that this probability is maximal. Therefore, this we want to maximize this likelihood, and that we will do with the performing the logarithm and then performing the negative logarithm, which we will see in the following slide. So once we take the negative log likelihood of a univariate Gaussian distribution, then we can see that it results into three different terms, where one term simply has some constants, another term has one parameter beta, and the third term contains both parameters beta and also the weights W, which lead to the mean. And this, we can see that here is the square term. And if we are interested in minimizing the error or maximizing the likelihood function with respect to W, then we can also just abstract from these additive constants, because here this the W is not changing, so the W will not be affecting these constants, and also the multiplicative constants like here the beta, and we will end up in a sum of square differences error for the error term for the vector of weights W. With the maximum likelihood estimation, we will be looking at minimizing this error term, and that will maximize the likelihood. And for the we will be looking for the weights W for which this error term is minimal. Once we find that, and while in the linear models for regression, we were able to find it in a closed form, here, in our case of neural networks, this situation will be more complicated. Nevertheless, once we identify the maximum likelihood of the W, we can then use it to calculate the maximum likelihood of the variance, which will be equal to the sum of square between the predicted values of the weights with the maximal likelihood minus the true values squared and sum, so sum of square differences normalized will be giving us the maximum likelihood of the variance. The reciprocal of it will become the maximum likelihood of the precision beta. Unlike the case of linear models, in the case of neural networks, our error function will not be a simple convex function, so that we can find its minimum by simply performing a derivative of this function and then searching for the value where this derivative is equal to 0, and by finding the corresponding weights W in this way. So in the case of neural networks, our error function will be much more complex and will be non-convex. In fact, the likelihood function will have several maxima, local maxima, and which will be corresponding to the local minima of the error function, meaning that there will be, in fact, many locations where the derivative of the error function will be equal to 0, but they will most likely be only local minima of this error function. You can imagine how this error function approximately looks like for neural networks if we look at this diagram showing this weight space. Imagine that we have just two weights, W1 and W2. So we have a two-dimensional plane, and in this two-dimensional plane we have all the possible combinations of weights having the coordinates W1 or W2 and W2. And the error term is somehow associated with each combination, with each vector W, and it corresponds to a certain error. And somehow this error function is placed as a surface over this weight space. Naturally, in our case, we do not have only two weights, but we have many weights, and in that case, also the error function with respect to W is also kind of above this. It's a kind of a hypersurface in this multi-dimensional space of weights. Now, in order to find the good candidate for the low small error, we will need to perform the iterative optimization in order to find the maximum likelihood of the weight vector. Now let's come back to the case of various examples of that will be that have a relation to the regression and the classification from the linear models, but now they will be applied to the case of neural networks. We will be discussing what are the individual error functions in these particular examples and what are the corresponding activations or activation functions. So now the second example will be when we have again a regression, but of multiple k target variables. This means that our vector t, or actually the value t, is no longer a scalar as it was before, but it is a vector. So, or a point in space, if you like. So the probability of a particular vector t given an x and some weights and some noise precision is again governed by the normal distribution, but in this case it is a multivariate normal distribution with the mean at the predicted point y, which have the same dimensionality as the vector t, and the as we are dealing with a shared noise precision beta, in this case, the covariance matrix of this multivariate normal distribution is in fact just a scaled identity matrix, where on the diagonal there will be always the same value, which will be the beta inverse. If we want to perform the search for the maximum likelihood of the vector of weights W, we can do it by, again, minimizing the sum of squares. So we have here the sum of squares. The only difference here that in this this difference here leads to a vector, which is then squared. So we will have again a scalar value, and we will have again sum of square differences, which we are trying to minimize by finding the best suited weight vector W, so point estimate. Once we find it, the noise precision can be determined by, or the noise variance of the maximum likelihood can be determined by the formula where we have again the sum of square differences, but not normalized only by n, but normalized by the product of n times k, where the k is the dimensionality of the target vector. We'll see also in the case of following examples for the classification. For both regression and classification, there is a natural pairing between the error function at the which is characterizing the error of regression or classification, and the output unit activation function. So not the activation function in the hidden unit or hidden layer, but in the output units. In case of regression, the output unit activation function is simply an identity. This means that the yk is equal to ak, so the activation itself. Therefore, the yk will take the values from -infinity to +infinity for the regression. The sum of square of this error has the following property. The partial derivative of the error with respect to the activation ak is equal to yk minus tk. So the predicted value yk minus the actual true value tk. And we will see that this partial derivative of the error with respect to activation for different error functions and different output unit activations functions will be the same. And we will utilize this fact in the case of the error backpropagation, which we'll be talking about next. Before that, however, we will be talking about the case of classification and where the activation function in the output unit will become a sigmoid, which is a sigmoid of the activation, which is the reciprocal of 1 plus e powered by minus a. And this y is at the same time equal to the posterior probability of class 1 given a certain input vector x. As we have a two-class classification, the probability of a class C2 given x is 1 minus y. And this leads to the probability, conditional probability of t given an input vector x and the some vector of weights w, that it is equal to y powered by t times 1 minus y 1 minus t. Meaning that if the x belongs to the category or class 1, then this t will be equal to 1, and this y will therefore be powered by 1, and this 1 minus y will be powered by 0. So this will be a 0, this will be a term 1 as a multiplier. And if the t will be equal to 0, meaning that the x is from the class C2, then this term will become 1 minus 0, will be powered by 1, and this term will be powered by 0, as we know. And this conditional probability of this Bernoulli distribution can be therefore also seen for repeated trials of n trials can be formulated as a product of these two terms and will lead to an error term which has the negative log, so the product will turn into a sum, the exponent will turn into a multiplier of the ln, and we will see here that for the two-class classification we have here this known cross entropy term. So our error function is no longer sum squared differences, but it's a cross entropy for the two-class classification. Now we will have another case of another example which we will be discussing, and that is the again two-class or binary classification. However, not for just one type of characteristic, but for case-separate characteristics. Imagine that we are performing three different classifications of a certain geometric object. Maybe the object has two different colors, or might have two different colors, either black or white. Maybe the object is small, or the object is white. The object is big. Maybe the object is circle, or maybe the object is a triangle. So we have three separate binary classifications. And in such a case, we will have a very similar situation as in the case of the two-class classification, only that we have it k times, and therefore the t here will become a tuple of zeros and ones. And as these are not mutually exclusive classes, because they are just simply different characteristics, therefore these t can have even values like 1, 1, 1, 3 times 1, or 0, 0, 0. So there is no constraint on how many zeros or ones it should have. Its conditional probability is very similar to our previous case. However, we have the product of the over k. So for each class, we either have 1 or 0 for the tk, and that will lead then to activating one or the other term. So, and that is just for 1. If we will have n trials of such a k separate binary classifications, then we will have a double product. And if we perform the negative logarithm of this in order to find the error function, it will lead to this, again, a double sum of the cross entropy terms here. And that error function, which will be measuring this, this error for k separate binary classifications, if we perform a partial derivative of this error term with respect to the activation, then as we have seen before, also in the chapter on classification, this partial derivative will lead to, again, yk minus tk. So the activation is with respect to one of these binary classification. So for the either the color or the size or the geometry, and before we put it into the sigmoid is the activation ak, and the error term partial derivative with respect to this ak is therefore the difference of the prediction of the classification and the true class. Now we will turn to the final classification case, which is the multi-class classification. The multi-class classification is also having a tuple of for t. However, as now we are dealing with mutually exclusive classes, we will be using the 1 of k coding scheme. This means that only one of these entries in the tuple t can be equal to 1, and the rest will be equal to 0. In this case, we are not using the sigmoid, but we will be using the softmax, as we know from the previous chapter and lectures, and we can formulate our conditional probability over t as the product over the k classes of our yk powered by tk, and then n times, meaning for all the training set samples. Now we can see here that this term is will be powered by 1 only once in this entire product, because for the rest the tk will be 0 and this whole term will be just 1 therefore. So it just chooses the yk value for which the true class is equal to 1, the tk is equal to 1. Now, that conditional probability can be then reformulated into the error term again as the cross entropy for the multi-class classification. And if we again perform the partial derivative of this error term with respect to the activation, we will end up in the same difference of the predicted value minus the true value, and as we have seen in all the previous cases. So while we had different different error terms or error functions with respect to W and different activation functions in the output layer, their combination will always lead to the fact that we have in fact the same partial derivative of the error term with respect to activation, which is simply the difference of the predicted value and the true value. As we have discussed before, due to the nonlinearity and due to the complexity of the basis functions, we need to resort to iterative approaches to find the optimal vector of weights W during the process of learning. So typically, we will be starting with some initial set of weights W, and in each iteration, we will perform a certain update with the delta W. This delta is often defined as the minus the gradient of the error or of the weights at the current time step. Minus because we are going against the gradient, and the gradient is pointing towards the highest direction of increase. With the minus, we are going in the highest direction of decrease of the error. Now let's have a look at our error term in terms of Taylor expansion series. We will just have the first two terms, the first order derivative and the second order derivative, as an approximation. So our error term with respect to the weights is approximately equal to some error term of the weights hat, which we know, plus the weights minus the weights hat. So this is the weights position we are interested in, the value of the error, and this is the offset vector times b, which is actually the first order derivative in this Taylor expansion series. So first order derivative of the error term. And then 1/2 and w minus w hat transpose h w minus w hat, which forms as the square term of having here the Hessian matrix. So so we have the B is the gradient of E and at the W hat, and H is the Hessian of E at the W hat. So it's a matrix, and this is a vector. Now, if we perform a derivative of the error at this point with this approximation, then this term will be cancelled out because it's just some constant. Then the W is here, therefore we will end up with a B here, and plus, and then we have the derivative with respect to the W here, therefore we will end up in this term. So the square term here will, after the derivative, will be having this term here. So we have then this as an outcome, which will be the approximation of the derivative of our error. Now we can use this for evaluating the error function near a certain minimum W star. So we know that there is a certain minimum W star, and we would like to characterize the error in the vicinity of this point at the coordinates of W star. So that is equal to, in fact, the error at the W star. Then the first order derivative is 0 because we are at the minimum, so the derivative at the W star will be 0, so we do not have the first order derivative term, and for the second order derivative we have the square term again. Now based on that we can analyze what is actually this term equal to, and in the sense this is just a vector, an offset of the W from the W star, and this vector actually can be expressed by some vectors which are like a basis vectors in that space. And if we look at the Hessian matrix and the corresponding eigenvalues and eigenvectors, these eigenvectors can in fact form the orthonormal basis, and the alpha I are just the coordinates in this space. So we can express this offset vector simply as a sum of the basis vectors, which are actually forming the eigenbasis in this case, each multiplied with some scalar alpha I, corresponding scalar. We can also see that the vector W is equal to the coordinates of the W star, in some senses the center of our new coordinate space, plus the coordinates in this eigenbasis of the W. So this is the origin now, and this forms the offset from the origin. That is like a change of basis here. Now also, if we express now the offset here through the eigenbasis, we can see that this square term here is equal to this square term here, and we can in fact put these two sums into like a double sum, so there should be two sums really, but they are just abbreviated. So we have sums over I and sums over j. So alpha I times alpha j and times, and then here we have the ui transpose h uj. Now, if we look at the orthonormal basis and the dot products, the dot product of ui with the uj is or either 1 or 0. It's only 1 when the I is equal to j, and if I is not equal to j, it is equal to 0. So therefore, we can see that only if the I is equal to j, we will have a non-zero term here, and therefore we can just cancel out one of the iterators here. But before we do that, I need to explain how we came to that, because we see here that the Hessian times the 1 times the eigenvector, it's in fact equal to the lambda times the eigenvector. So therefore we can replace the h with the corresponding lambda, then we have a scalar term, and then we can actually perform this dot product between ui and uj. And therefore, we will end up only with I equals j non-zero terms, and therefore the outcome will be the sum over I alpha I squared lambda I. And therefore, our error term, W, will be approximately equal to the error term at the minimum plus the sum of these terms, meaning the scalar multipliers associated with each eigenvector squared times the lambda, the corresponding lambda term. Finally, we can also define that a stationary point like the W star will be minimum in the multidimensional case if the H, the Hessian matrix, is a positive definite, and which also implies that its eigenvalues need to be positive. Why is that the case? Well, the definition of positive definiteness of lambda is that for any vector, if we perform the multiplication of the row vector times the Hessian matrix and then the consecutive multiplication with the column vector, we will end up with a scalar value which should be higher than 0. And then that means that this is the positive definiteness, and the W in the space of the eigenbases can be characterized as the sum of the eigenvectors, each associated with a certain scaling factor Ci. And if we have the therefore the formulation as we had on the previous slide, we'll find out that this term, this multiplication of a matrix with the vector and then consecutive multiplication with the row vector will give us a scalar value, which can be calculated as previously. So it's a sum of lambda I Ci squared, where the Ci's are these coordinates. So this term, in order to be positive, this term will for sure be positive because it's a square, and therefore this term needs to be positive as well, so that we will guarantee that this term overall will have a positive value. And therefore, the positive definiteness implies positive eigenvalues of the corresponding to the Hessian matrix. Now we can have a look at the corresponding space which we have defined. So if this is the Hessian, the eigenvalues are positive, this will be a minimum, local minimum at least, and the error terms will be somehow of identical values along these ellipsoids in some high dimensional space. So here we have only two weights, weight 1 and weight 2. So, but normally we will have much more weights, and in this high dimensional space, weight space, we will have an ellipsoid, and in each direction there will be slightly different change of the error. Sometimes more abrupt, like in this direction, sometimes more slower, like in this direction. And that's, we can find these contours of the same error around our minimal error. It is important to state why it is meaningful in terms of neural network training to use a gradient in our calculation of the weights update. Well, if we have our quadratic approximation of the error function, then the error surface is specified by the W times the W plus 3 divided by 2 parameters of B and H, with W being the dimensionality of the W, so how many dimensions the W vector has. Now, the W has the dimensionality capital W, and the same dimensionality has also this gradient vector B. And in order to approximate the change of error, we need both B, as we have shown on the previous slides, and we also need the Hessian matrix. For the Hessian matrix, if we would be interested in the matrix itself, we need the W squared of information. However, we know that Hessian matrix is a symmetric one. Therefore, for a symmetric matrix, we need only W times W plus 1 divided by 2 parameters, because we only need the diagonal and one of the half of the above the diagonal, let's say, because the values below the diagonal are the same as the above diagonal. And therefore, in total, together with the vector b, we need to store the w times w plus 3 divided by 2 parameters. So that means when we are performing the calculation of the change of error and approximating this change of error by the previous derivation, where we had the b plus the h w minus w hat, where the w hat was the previous position. Now, in order to find the location of minimum, without gradient and Hessian, we will need to use something like finite differences, and in that we will need to, for each dimension, we will need to evaluate the error around our point w hat. So we will need to perform overall at least w squared calculations if we want to perform furthermore the Hessian approximating for calculating the derivative of the error. Then we will need at least the complexity of the w powered by 3. So this is a cubic complexity. And if we will have the gradient information, and we will in the next be talking about how to calculate it with for example, back propagation efficiently, then using this gradient information can be we can find the minimum with a complexity proportional to w squared. So one order of the of magnitude complexity less than without having the gradient information available. To iteratively obtain the weights W for the entire neural network, both for the hidden and also the output layer, we will be using the update using the gradient descent. So the delta W update here will be composed of a negative gradient of error with respect to the vector W, and which is scaled by the so-called learning rate, and we have the update in the negative direction because the error gradient is pointing towards the highest change, towards the higher error. So minus secures that we are pointing to the minimal error direction, and this is how we perform the update. Here, in this case, we are having an error term which is containing the entire data set. So in fact, the entire data set is necessary to go through for calculating the gradient of error with respect to the weight W. Now, this could be a lot of entries. It could be also the full data set when and we call such methods where we use not only just one entry from the data, but all or at least some sizable amount. We call them the batch methods, and we will refer to a parameter during the training, what is the batch size. And but this is not the only way. We can also have the approach where we have just the one data point and measure the error with respect to the weights with respect to this one data point. We will come back to that soon. However, if we are dealing with the batch methods, it's important that we perform this search for the minimal weights not only from one starting point, but also we perform initialization at multiple points and run the optimization multiple times so that we have a chance to end up in a more favorable local minimum throughout this process. However, what would be a more popular method instead is to use the online or gradient descent or sequential gradient descent or stochastic gradient descent. Under all these three names, this technique is known, and this technique takes only one data point into account when calculating the error, and it is in that respect less demanding in terms of memory, it's more efficient, and it's less prone to get stuck in a local minimum. So it takes less memory because obviously we do not need to store the entire data set, but just one data entry and associated values with that. Second, it is more efficient because imagine if we will just double the data set size, then suddenly we will have double requirements on the memory, but also we will need double time to go through and calculate the error. However, with this stochastic gradient descent, nothing will change much because it will be simply going through this data set one data entry at once, and the picking of the entries from the data set will be performed in the randomized way with repetitions. And why is it less prone to end in the local minimum? The reason is that the stochastic gradient descent from this one entry is having an error pointing in general not in the same direction as the global entry from or error from the entire data set. This means that if we are stuck in some local minimum of this error for the entire data set, the stochastic gradient descent calculation of the error with respect to the weights for that particular data point or training set point will be pointing somewhere else and might get us out of this local minimum. Overall, our reasoning is based on the fact that the change of the error or gradient of the error with respect to the weights W is equal to the sum of the gradients of the error of all data points with respect to the weights W. So, and here finally is the formulation of our stochastic gradient descent, where the new weights are calculated simply just by the error term or gradient of the error term based on one data entry. Now we know how we will perform this update of the weights, and we will have the entire gradient of weights, or actually, sorry, the entire vector of weights stacked in one long weight vector across even various layers. They could all can be just stuck into one big vector, and our gradient will also be such large vector, and will be containing the error gradients with respect to various position of the weights in our network architecture. So, and there are several ways how we can calculate now this partial derivative of error with respect to the weights. And some methods are more of a numerical character, like, for example, finite differences or central differences. We will be talking about them later. but here we will be talking about the most efficient method for calculating the error change with respect to the weights, and that is the error backpropagation method. So we have our feed-forward neural networks, and if we are calculating we enter a data point into the network, and then we calculate based on this data point what are and given the trained weights, what are the hidden unit values, and then the activations of those, and then what are the activations in the output layer and the corresponding output values, whether this is for regression or classification. So we can use the so-called forward pass. So we are starting from the left conceptually on the network and then propagate our input vector through this network and get an output. As the name says for this method, it's called the backpropagation, so we will also be going in the opposite direction. It's an efficient method for calculating the gradient of the error function E of W. However, it requires not so demanding, but still some memory requirements, and it will only consist of one forward pass through the network and one backward pass, and we will talk about the computational complexity just in a moment. So it is useful for calculating the gradient of the error function, but we can also use it to calculate Jacobian matrices or Hessian matrices, which are containing the either multivariate derivatives or second order derivatives. And if we are evaluating the error of the with respect to one data point, that can be used directly for the sequential or stochastic gradient descent. And in case we would like to perform the standard gradient descent, then we can use the calculation of the error with respect to one data point or training point, and we can sum it up in order to calculate the overall change of error derivative, and then after we have this value or this vector available, we can perform the gradient descent. So let's start with some conceptual understanding of this backpropagation. Let's just recap some basic understanding. If we have here like a very simple linear model where we have various input point values x, and then we have some weights which are performing then the linear combination of these entries of x, so x0 to xd, and the sum and the linear combination of those forms as the outcome y k. It's not exactly the same shown in this network diagram, because we have here a linear model, and here we have a hidden units layer, which we do not have existent in this expression. However, we can see that the points x are starting like from xi is equal to 0 to xd, so it has d plus 1 entries, where the x0 is equal to 1, as we know, to take into account the bias. Now, then we have these weights ki. So here there would be always the second index is associated with the input, and the first index is associated with the output. So the WKI is a scalar value of the weight, which is an entry, of course, in the large weights gradient, and it is telling us where does it go to and where does it come from in terms of our units within our network. So here we can see that this is a contribution of xi. Let's say the I is 1, then it will be from x1. And the weight is essentially connecting with yk. Let's say k is capital K, so then this x1 will be connected, so forget about this hidden unit here for this drawing, will be connected to this yk, and this connection will be basically expressing the weight. And naturally, this yk is receiving, the capital K in this case, is receiving contributions from, or is affected by, values from different entries I. So here we have, in this case of this layered network, we would have like a, if it's fully connected, then from this entire hidden layer, all units of them will be contributing to a y capital K. So this is this iterator, which is then securing that we are summing up all the contributions from and weighting them with their respective weight. If we are performing a error quantification in this simple linear regression model, we can use the just the sum of square differences. And here we can see that the sum of square differences is expressing the difference between the y, so the output of this neural network, and also the t, which is the true value which we know in for the training set. So that leads to the known sum of square differences. Just observe that we have n here and n here, so that relates to the fact that we have we put into the network one xn, and that xn is one entry from our input vector data, and under this, that one is associated with a certain Tn, and this Tn has various entries, coordinates, or components, this Tn vector, which have the same number of components as the y, so it is capital K components, and this k, small k, is simply an iterator which goes over this over all k's. And the same holds, so this is just one component of the Tn vector which corresponds to the xn, and y is the nk is the corresponding output value, which ideally should be the same or very similar values. So here you can see once again that T and K is like YK, so here, and which is based on the input vector xn and the weights W. If we will be performing the evaluation of the error derivative of this sum of square differences, and we have done it before, we will find out that the change of error with respect to the weight ji, so this is like where the W connects on the right side. This is where the W connects on the left side, and the previous layer is equal to, we simply perform the derivative of this formula with respect to the weights W. So, or in particular with respect to this weight, and the weight is included in the y here. So first we perform the derivative of this expression here, which is simply 2 times this term, and then we have all the vectors or the weights. They are in fact constant, because in this partial derivative scenario, in this partial derivative case, so they all will be in fact, as they are constant, this term will be equal to 0. Just only that term will not be equal to 0, which actually contains the wji. And the wji is associated, is calculated from the for particular y, and there it is associated. So here it will be with yj, because we have here j, and it is calculated from the xi, and this term will be the only term which will not be 0 throughout this derivation, and deriving with respect to w, xi will lead to the xi. And here we have also in the indexing we have the n, because we want to stress that this is just coming from one single data entry from the entire data set, which is indexed with the small n value for all of these 3 or 4 quantities. So this is how we can calculate this change of error with respect to one particular weight, and we can do it for all weights, and with that we will obtain the large gradient of error with respect to the weights and for a particular input, and that can be then used for together with the learning rate for updating the weights W. While this is not telling us much about the back propagation yet, it is telling us about how we are in principle obtaining these entries within the weight or change of error with respect to weights gradient, and we see that we have here somehow an isolation of certain terms, and this term, for example, here we will be calling an error signal associated with the output end of the link wji and the input end of the link x and I. So that's this error, and this error has this form for the sum of square differences. However, for other error forms, it will have different functional formula. However, it will simply have the same kind of there will be the same structure in principle. Let's have a look at this and at this more general case. So in general feed-forward network, the forward propagation is that we are starting with, let's say, the input. The input is then multiplied with the corresponding weights and leads to an activation or pre-activation, if you like, as an argument to the activation function, which is in general nonlinear, and leading to the new variable zi, which could be, for example, which is the hidden layer unit value. And then this this can be seen in a more general way. Imagine that we have several even hidden units, and in the beginning we will have the input vector xi, but after this first calculation and multiplication with the corresponding weight, we will have more of this kind of formula where we have in one previous layer the activation, so the z, which is the pre-activation, so the weights multiplied with the even previous layer and summed up is an argument to the nonlinear activation function. As an outcome, we have the hidden unit value z. And let's say we are in the first hidden layer, and we are going, let's say, either to the output or the second hidden layer, and then we can see that this activation becomes an input or an argument for the activation calculation for the next layer, and that is done through the multiplication with the corresponding weights, which characterize how is this variable influencing the next layer's unit j. And we go over all the units which are connected with this value j, with this unit j. So therefore, again, we can see here that the weights j is telling us what is the next layer, the target layer, and the I is telling us what is the source layer where this information is coming from the left side, so to say. And now the derivative of the error is calculated with respect to various quantities. Ultimately, we are interested in the derivative of error with respect to the weights, because that is the gradient we want to calculate for our stochastic gradient descent. However, before we have can do it directly, we have to do it by a chain rule. So the chain rule will secure us that we have here the error with respect to an activation, and then the activation with respect to the weights. So for example, if we have here the error with respect to the activation, and we will have the error measured by sum of square differences, and this is the activation in the last layer where the activation function h is equal to identity, then this will be simply what we had in the previous slide, which will be the yk minus tk, or better to say j, because we have index j here. And then that is multiplied by the derivative of the a with respect to the weights, and that is like, imagine that we have this, let's say we are in the last output layer and some unit j, and that is connected to another previous layer, and in there to a unit I, and we want to know what is the change of aj with respect to this weight. And it is in fact, as we have this formula here, it is in fact the zi, the activation from the previous layer, which is characterizing this derivative. So the overall formula for characterizing the how does a certain weight entry influence the error, which is what we are searching for, can be expressed as this error term and the variable from the previous layer. So we can see that we have this in general. We have this error term here expressed by this delta, and j, because it is related, this error, to the unit j, and is multiplied with the connected activation in the unit I, and it's connected exactly through this weight ji. So, and now we can have this delta I mentioned. It could be like just like yj minus tj for the case of sum of square differences. But in general, this is an error which is different for every error function. So let's have a look. Sorry, for every activation function. So let's have a look how we calculate it. So in this case here, we have a schematic diagram where we have our, so the feed forward network goes this direction, and we have here, let's say, this output layer, which is having the values y1 to yk, and each of these units for a particular input value, input data point x, we will calculate the delta 1 to delta k, which is expressing the error, and then this delta k is multiplied for finding out how much is this weight influencing this error. It's multiplied with the previous, with the value in the activation, in the previous activation. So, and that is now, so this principle is now calculating, for example, the error delta k, but for example, we can see also how does the error with respect of this one data point caused by this one data point, how is this weight affecting it, this ji here. So in this example, we can see that it is affected by the error delta j times the zi, which is again in the previous layer. So we can see that how this formula basically works in principle, and now we need to find out how do we calculate the, so we calculate this zi, zj, and yk in the forward pass. We simply calculate all these values from the left to right, and from the right to left we need to calculate the and that's why we need to store them, and from the right to left we are calculating these delta values, these errors. Once we know what error has been actually caused, because we the y value is confronted with the t value, with the target value for that corresponding data point, then we can backpropagate these errors. That's why it is called error backpropagation. So as I said, for the linear model, this delta k is equal to yk minus tk here for this node, both in terms of the case that there is no activation, I mean there is the activation function is identity, and the particular error quantification is the sum of square differences. So now let's have a look at the more general formula. How do we calculate the derivative for, or how do we calculate this error? So in general, for the hidden unit, we need to calculate the derivative, and based on the principle that the variations of aj give rise to variations in ak. So if we change this j values layer, some different activations are here, they are influencing the kth layer. So let's define that the error delta j is equal to the change of the error with respect to the activation j. So, and now, in this case, with respect to, if it will be change of error with respect to k, well, in that case, we simply can use something like this if we have the sum of square differences, as I said before, but we do not have the direct connection between the error and this activation j here. So therefore, we need to quantify what is the change of error with respect to the activation k, and then what is the change of activation k with respect to activation j. And that furthermore is because they are also not directly connected, because one is directly connected to the z. So this is the after aj is before applying this nonlinear let's say a sigmoid function or tangent hyperbolicus function, and the z is after. So change of a with respect to z in the previous layer is something what we can express, and then we can also express what is the change of z with respect to the a with the same index. So we said, what is this? This is, again, by this definition, this is equal to, with this index, delta k. So this term here is like giving us this value, but not j. Here j is here, that's why this is j, but here is k, that's why this is equal to delta k. So we have a delta k here. So the delta j is equal to sum of all delta k's, so of all delta errors which are being influenced by this node, and then the partial derivative of the ak with respect to zj is so here is the activation k, and here is the zj. So it's this derivative is actually the w here, which is the wkj, and then the partial derivative on within the node of the post-activation with respect to the pre-activation is the actual nonlinear the activation function and the derivative of that, which is this h prime aj. And this is the general formula for calculating our error term. And once we have this error term, we can calculate the entry in the gradient vector of the errors with respect to the weights, because we have, like, here is the delta j, and we just need to multiply it by the zi. So here is the overall formula, but it's generic because it's recurrent. First of all, it will call up for the previous errors from the later layers. It is containing the weights, and it is from the current iteration, because we are in the training of weights, so in the current iteration, and then it is also dependent on the derivative of this activation function and at that particular node. So now, once again, let's recapitulate this simple and yet powerful approach to calculate the derivatives. So the derivatives of error with respect to the weights, this is what we are interested in, and this error function with respect to weights can be calculated as the error term from where we have obtained that calculation in the just in the previous slide, and times the activation, the value z, which is which this weight we are performing the derivative width is connected to. So first, for this algorithm, we make the forward pass. And in this forward pass, we will, for a particular vector xn, we will propagate through the network and calculate all the activations for all the hidden and output units. So we will have all the x values given because it's a training set, and then we will calculate the values zi and y and cj and yk, depending on how many hidden units we have. Then first we calculate the delta k, which is the error of partial derivative of the error function with respect to the activations k. So that is taking into account the derivative of the nonlinear activation function, and it is also taking into account what is the derivative of the error function itself. Like in this case, this is the result of this delta k term for the sum of squared differences and the activation function being identity. Once we have obtained these errors for the entire output unit, we can backpropagate it to one layer before in order to calculate this delta in the layer J. For that, we already know all the delta K's. We also know all the WKJ, the weights from the previous pass, and we can also calculate what is the particular value of the derivative of our nonlinear function for our pre-activation J. So with that, with this sum, so we have now taken this derivative out of the sum because it's not dependent on k, and just as a multiplier, and then once we perform this backpropagation, we can find out all the values of this delta j in the previous layer in the feed-forward network. If it's just a two-layer network, it will be the only hidden layer we have. And once we have calculated for the two-layer network, the delta k and the delta j's, so the delta k's for all of these and the delta j's, which are all of these, then in such a case, we can calculate the overall gradient where we are multiplying these deltas with the corresponding input to that particular unit, which is connected by this weight again. So we always need to look at these indices. This is the one where it's connecting to, and this second one is where it is connected from. And once we have all these components of the gradient, we put it into the as values of the overall gradient and can perform one pass of the stochastic gradient descent. In order to even better understand the concept of error propagation, let's just go through it on a simple example of a specific network with a specific error and a specific activation functions. So in our example, we will have a two-layer network, which is fully connected, and it has a sum of squares error with the output unit has a linear activation function, and the hidden units have a sigmoid-shaped activation function, which is the well-known 10H. So it's not a sigmoid function, but sigmoid-shaped 10H 10H, which in principle has the same properties as it also maps the real axis onto the interval 0, 1, where the 10H0 will be equal to 0.5. 10H is has been frequently used as an activation function, although maybe these days not as frequently used, but it has been frequently used at the past at least. So this will be our hidden unit activation function. The 10HA has the following formula. It's basically an exponential function and a ratio of exponential functions, where we have in the numerator e powered by a minus e powered by minus a, and in the denominator we have e powered by a plus e powered by minus a. The nice and convenient property of this activation function is that h prime a, so 10h derivative, is equal to 1 minus 10h squared. So we will be making use of this in our formulas. Our function for the sum of square errors is depicted here, as it measures the error given a input vector xn. So first, as we said, we want to perform the forward pass and calculate all the values which are associated with the forward pass. Therefore, we will be first computing the forward pass, and in that forward pass we will be concerned with the activation, which will be the activations in the hidden layer, where we have the weights connecting the input xi with these activations aj, and we can see here that here is a sum over all components of the input vector xi and their associated weights, forming the linear combination of the x vector components, forming us the value for the activation. The activation aj is then stored along with the post-activation or the outcome of the activation function 10h aj. So here we can store both, and also once we have these two values, the zj, which will become the input for our output layer, where it will be again we will be performing a linear combination of the vector z components weighted by the weights kj, forming us then the resulting vector y as an output vector. From here, we can see that the input vector is d-dimensional, so we have d dimensions for the vector x, and here, as we are going over z m times, or including 0, so we have the vector z will be m-dimensional. The yk is one component of our k-dimensional output vector k, and we can see on this another sum here that the y has a capital K dimensions. So once we complete this forward pass here, we have available the all the activations, post-activations, and output values. And now we will need to initiate the back propagation pass, where we will be calculating the errors. So first we calculate the error on the output layer, where for each unit k, we calculate the delta k. As we are dealing with the sum of square differences, the error or the change of error with respect to the weights here, or change of error with respect to the activation, is equal to yk minus tk. And that is giving us the weight, the errors for the final output layer. And once we have computed all those, we can calculate the errors for the hidden layer. And the values for the hidden layer will be calculated based on the specific form coming out of the generic formula, where we have here the derivative of the activation function in the hidden layer, which is in our case 10h, and 10h derivative is 1 minus 10h squared. Therefore, we are seeing this form here, and then we have the other terms from the generic formula, where we have the weights kj, so connecting us between the delta k errors with our units in the hidden layer, the j units in the hidden layer. And for a specific delta j, we go along all the outputs and collect essentially the information, how much are we influencing with our jth unit the k units in the output layer. That is expressed by the overall error of that particular unit, and the weight, which is giving us the information how much is this delta j affecting the unit k. And with this backpropagation, we therefore obtain the values for the delta j. So with this formula, we can calculate all the errors within the hidden layer. And once we have those, then we can just calculate the partial derivatives of the error term with respect to the weights. And in the first hidden layer, we can calculate this by multiplying our errors in the jth nodes with the particular input I component, as basically defined by which weight are we looking at. So in this case, this is the ji, and therefore we are looking at the jth hidden unit and its error, and we are looking at the input value at ith component of our input vector. And then this is one part of our gradient of our error with respect to weights. And the second part is defined from the output layer, so where we have here our weights, our errors from the output layer, and this is multiplied by the inputs coming from the activations coming from the hidden layer, and therefore the delta k zj is the term, provided that we are looking for the influence on the error of the weight kj. So now with this, we will be computing the second part of our long gradient of the partial derivative of error with respect to the weights. And once we have it completed, then we can calculate our stochastic gradient descent, one step, one iteration with it, and update our weight W, so that we can again perform the forward and backward pass for the next data point during our training process. To consider why are we performing this backpropagation in order to obtain the gradients. Isn't this another way how we can calculate gradients, so let's say with numerical methods? Yes, there is, and we can contrast or confront the backpropagation efficiency with these methods. So let's first think about what is the efficiency of backpropagation. So backpropagation, as we have seen, needs one forward pass during which we calculate our activations A and the post-activation C, and also the output layer Y vectors, and we store these. And once we have these, that is just one pass through the network. And then we perform the backward pass where we are calculating these errors. And once we have those, we can calculate all the components of our partial derivative of our gradient of the error with respect to the weights. So we actually need two passes through all the weights in order to perform the backpropagation calculation to obtain our gradient. And that is proportional to the computational complexity of W. Now, in case of finite differences, which would be another approach, we can, which is explained here. So we have here our partial derivative, and the partial derivative is calculated as the error of the with the weight Ji plus some small epsilon, small perturbation, and then minus ENWJI. So we are looking how is the error in the behaving in the closed neighborhood, and by subtraction we are performing this difference, this finite difference, and this is then divided by the denominator, and this is just a numerical solution. We are having here some additional error term associated with this approximation. So this looks very simple, and it is conceptually very simple. However, computationally, if we think about that, we need to, for every of these WJI, we need to solve this this formula. And so we need to do it W times, and because this amount of total gradients. And here we also, as we are calculating this WJI plus epsilon, we in fact need to go through this through the entire network and calculate in order to calculate this error. This error we can have just maybe calculated once as a basis, but this error, when we are always changing this one component by an epsilon, we have to recalculate from scratch. And that itself has the complexity of OW. So we have, like, for finite differences, we have to do W times OW plus 1 for this one, and this will overall be the complexity of OW squared. So this is quite a complex process, and if our gradient is has several millions of entries or even billions, then making a complexity squared will make out of it a completely intractable approach. Then compared to finite differences, more popular are sometimes the central differences, which lead to a more precise numerical approximation of the gradient, because they not only perform a slight perturbation in the forward direction from the weight position, but also in the backward. And that's why we are here performing the subtraction of these two terms, which then leads to the fact that we need to calculate for each of the passes, which is for each of these calculations of W, we need to calculate this, go through the entire network once and twice here. And so we have twice the complexity, and we need to do it W times. So we end up in O of 2W times W, which is proportional to O W of squared, which means that we again have the quadratic complexity, and that makes again this solution intractable for more complex or longer gradients. It needs to be said that, however, for smaller gradients, this might be an interesting idea to just calculate the gradients and see whether the gradients are the same as the ones from the backpropagation, because we might need it for some debugging purposes. Here, in the central differences, our residual error is actually smaller than the one from the finite differences. So this is maybe not the more efficient method, but it is certainly a more precise numerical approximation. So now we effectively have learned how we can use the backpropagation in order to calculate the weights in an update of the stochastic gradient descent. This is not the only utilization of backpropagation. We can use backpropagation in calculating the gradients of for other reasons, and by using this chain rule embedded in this backpropagation principle. So, for example, we can calculate the Jacobian matrix, which can be useful if we want to generally understand the sensitivity of a given system. Imagine that we have a system, maybe as it is depicted here, where we have some kind of various variables, and like, for example, this input here and this input here is combined with the weights in order to generate us this value z, or maybe there is an activation function which generates this value z, and then in each of these boxes there is some kind of weights are multiplying our components of the input, and then some activation function is then applied to that. And we would be interested to see how in such a system the y is affected by changes of x. For that, we will need to calculate the Jacobian matrix, which will contain all the components of the output in the rows. So there will be capital K rows, and there will be I columns expressing the partial derivative of the yk with respect to the xi. So this Jacobian matrix will be a matrix which will have these derivatives of vectored valued output with respect to the vector valued input. And for the sensitivity analysis, if we would just change our xi just by some small value, or we will have some small value of xi here, we will see how does that small value affect the value at the output. So this is how the sensitivity analysis is performed. Or we can also understand how can we, for example, express this Jacobian matrix in order to have it as a building block of more complex derivatives. Like, for example, here, already in the backpropagation partial derivative of error with respect to weights, we had here a double sum over k and j, and then we had here the error with respect to the y and then y with respect to the z. So basically what was going on here with the is expressed in this term, and this is in fact, if we have a lot of z components and y components, this will be forming us a Jacobian matrix again. So we can see that the Jacobian matrix can be utilized in many contexts here, and we would like to therefore use an efficient method for calculating it. And backpropagation is a good candidate for that. Now we can calculate the Jacobian, and here we have the Jacobian, which, as I said, is JKI. This is one entry of the Jacobian matrix, where the K is the index of the row and is associated with the output, and the I is index of the column and is associated with the input. However, now we have like again a two-layer network where we have the YK characterizes the output as we had it before, and we want to have the understanding of how the output in this two-layer network is affected by the inputs. So for that, we calculate this is equal to the derivative of yk with respect to aj, which is now the activation of the hidden layer, and then we have the partial derivative of aj with respect to xi. So this is essentially giving us the this partial derivative, and in a sum. So for all j's which are connected to the yk, and they are connected to the xi. Now we can look at these two terms, whether they are already expressible, and we can see that this one is how we can calculate the activations with respect to xi. Well, the aj is calculated as the sum of the weighted xi's. Therefore, this partial derivative is the weight itself, and only the weight where the aj and xi are the indices, because for all the others this weight will, so all the other x's that will be treated as constants. Therefore, we have already solved the part of the problem, finding out what is our Jacobian matrix entry equal to. So it is a sum of these two terms, and we already see that the weights are showing up here. And what is this term? Well, this term is we need to look how we can obtain its value. So now the slight difference is that we do not have just identity activation function, but we have sigmoid at the output unit. And the sigmoid at the output unit is, we know that it's partial derivative of yk with respect to al is equal to, and here we have the yk times 1 minus yl, where this ikl is entry in the identity matrix, which is 1 only if the k and l are the same value. So if l is equal to k, and then so this derivative here is 0 for anything else except if k is equal to l, and in that case it is equal to yk minus yl or yk minus times 1 minus yk. So so we can see that this is the output. This is the derivative, and we will use this information because the partial derivative of yk with respect to aj is equal to sum over all the partial derivative of yk with respect to al, and then partial derivative of al with respect to aj, where the al is are the activations in the output units. Now this turns out to be the therefore we have like the calculation of the partial derivative, which we have here. It is written in a slightly different form. So this is this, but only so we have here a KL, only if the K is equal to L. So while this is a sum here, it will only be true or non-zero for if the K is equal to L. And then this is 1 here. This will be then the sigmoid derivative of AL, which is equal to yk1 minus yk will be here. And then we still have the partial derivative of AL in the output unit with respect to the partial derivative of Zj in the hidden unit, and then partial derivative of Zj in the hidden unit with respect to the pre-activation, and therefore the overall partial derivative of yk with respect to aj is the derivative of the sigmoid just for 1L though, and then the WLJ, which is coming from this term here. So this is the connection between the output unit and the hidden unit through this weight, and then this term will be simply the derivative of the hidden unit at the activation AJ. So with this, we have calculated our entry, or the second term, for our Jacobian, and we can see that here this term then will be, while it is sum itself, it will just be one term eventually. Therefore, the jki is equal to the sum of the j, as we have it here, of the wji, and then h prime aj, and then we have the yk 1 minus yk times the wkj. We also have here an example of if the output unit activation function would be a softmax. And in such a case, we have here that the yk partial derivative with respect to al, so the activations in the output units, is equal to yk and times the identity matrix entry KL minus YL. So it is either equal to YK1 minus YL, or it is equal to minus YKYL if the K and L is not equal to the same value. So in such a case, we will therefore have the two sums, and therefore the structure will be a little bit similar. We will start with Wji weight and then H prime Aj, but here we will have retained the sum, which will be the IKL YK minus YK YL, because we have multiplied out this term, and times the WLJ. So with this, we have been able to calculate all the entries in the Jacobian matrix, expressing how the input is affecting the output. So once again, we can recapitulate how we can calculate the Jacobian. Using backpropagation. So again, similarly to the error backpropagation, we can calculate it by first for each xn, just go and make a forward pass where we are calculating all the activations and the output values. And then for each row corresponding to yk, we can backpropagate in order to find all the Jacobian entries in the hidden layer, and then we can perform the backpropagation to the inputs and to obtain finally the final value of the Jacobian value entries y with respect to x. For several approaches in neural network training, we will be utilizing also the second order derivatives, not only the first order derivatives, such as the gradient, and therefore we will be discussing now the Hessian matrix. The Hessian matrix is a matrix which contains the information about the second order derivatives. We will be looking into second order derivatives of our error of the network with respect to particular weights. And as we can see, we have here the second order derivative of the error with respect to one weight, and here partial derivative of another weight. This could be the same or a different ones. This could be coming from various parts of the network. It can be either from the weights related to the hidden layer or weights related to the output layer. And we will show several techniques in the next a couple of minutes on how to perform the calculation of the Hessian using backpropagation, and also how to use the Hessian matrix, what type of approximations of the Hessian matrix can we imagine to work with instead of the full Hessian. The full Hessian matrix has a certain computational complexity to compute, which is generally higher than if we are looking at the exact values as compared to the approximations. So what are the uses of the Hessian matrix in general? We can use it in nonlinear optimization algorithms for network training. So instead of only relying on the gradient, the first order derivative, the Hessian matrix can tell us about the curvature of the error surface and lead us to the minimum in additional way. Then it is also Hessian matrix is a basis for fast procedure for retraining a neural network based on few new data. Hessian matrix can be useful, or better to say inverse of Hessian can be useful for pruning neural networks and removing some insignificant weights. And the inverse of the Hessian will guide this process. We have seen that the Hessian matrix is useful in the Laplace approximation in general, and in particular we will be using the Hessian matrix calculated from the neural network in the Bayesian neural networks in a moment. In the following, we will be discussing various approximations to calculate or represent the Hessian matrix. One representation, which is perhaps the most approximate one, a very rough approximation, is a approximation of a Hessian matrix just by its diagonal. So it's an diagonal approximation, and in there we are looking only at the terms where we have the entries of the second order derivative or the partial derivatives within the Hessian matrix along the diagonal, where it is twice derived by the same weight. In this case, our weight is indexed with two indices for the reason to indicate which layers in the network it connects. However, we will simply just stack these weights into one weight vector from all the layers. In our standard case, it will be the two layers, one hidden layer and one output layer. And therefore, we will just treat this as one component of this weight vector. Now we would like to therefore know what are the values along the diagonal, and we can consider first the case of the second order partial derivative of the error with respect to the weights kj, which means that the weights which are located between the or connecting the hidden layer with the output layer. And therefore, this can be represented as a first order partial derivative of our error in the output layer times the zj, the post activation from the hidden layer, and that is because we had this definition that the first order derivative of error with respect to this weight is exactly this term. And if we want to obtain the second order derivative, then we have to perform this derivative once again. Now, if we perform this derivative, we can see that here is the partial derivative of the error delta k with respect to the wkj. So this is now derived, and this is not derived in the product derivation rule of a product. And then we have here the other constellation where we have partial derivative of z with respect to the weights kj, and the second term is underived. Now we can see that this second term, where we have this zj, is not really dependent, is not affected by the weights itself, and therefore this derivative is 0. So only this term remains. So, and this term we can further represent as the partial derivative of the error with respect to ak, and the partial derivative of ak with respect to the weight. So this is the activation in the output layer, and of course times zj is here. However, this this term, this partial derivative, is also Zj, and therefore we will have the outcome telling us that the partial derivative of delta k with respect to ak times Zj squared is the second order derivative of the error with respect to the wkj squared. So, and then furthermore, we can look what is this formula equal to, and this formula is equal to the error yk minus tk, and with respect to the ak. And now, depending on the activation function, we will have different outcomes. So for example, for the linear activation function, where the ak is equal to yk, and under the sum of square differences error, as we are used to in combination with this activation function, we have that this term is this term where the ak here is yk, and yk with respect to yk, and here is a constant, is equal to 1. So this second order derivative, in fact, for the weights which are related to the output layer, are equal to 1 for the linear activation function. For the sigmoid activation function and cross entropy error, we would have that this term here is equal to this term, and if there is a sigmoid, then the derivative of sigmoid is sigmoid times 1 minus sigmoid, and the yk represents a sigmoid where the ak is its argument, and therefore this is again a constant. Therefore the result here is the sigmoid derivative. Therefore this will be the outcome of the second order partial derivative with respect to wkj squared, or when we have the sigmoid activation function and the cross entropy error. Now, these were just the weights from the with respect to the weights in the last layer, which we need to consider. And now let's have a look at the weights which are coming from the related to the hidden layer. So these are the weights ji, because they are connecting the input with the hidden layer, where the input we typically index with I, and the hidden layer we typically index with j. So this partial derivative, second order partial derivative, is similarly equal to the first order derivative of this term, whereas this term is exactly the error with respect to the partial derivative of the error with respect to the wji. And again, this can be represented as a product, derivative of a product. However, this one element in the product, where we partial derivative of xi with respect to ji weight, is in fact 0, and therefore we don't list it this time here, and we have only the part which is non-zero. This term we can further decompose into the error j with respect to ij, aj, and the aj with respect to the wji, and therefore we will have that our outcome for this weight is the partial derivative of delta j with respect to aj times xi squared. So these are all only the second order partial derivatives on the diagonal of the Hessian matrix. Now, we already know everything about the terms from the weights, output layer weights. Now we still don't know what is this term, and let's have a look at it and calculate it on the next slide. So now we need to find out what is the partial derivative of delta J with respect to the AJ, and we already know what is the delta J from our previous discussions on backpropagation and in our two-layer network. And the outcome is that the delta J is equal to the H prime AJ, which is the activation, the first order derivative of the activation function in the hidden layer, times the sum of the WKJ and the delta K, we could say, or the partial derivative of error with respect to AK. Now, if we perform a derivative of this term with respect to AJ, that is equal to the derivative of a product. So first, our product will have two terms, and the first term, the first part is the derived. So here we have the second order derivative of our activation function in the hidden layer, and times the underived part, which is this one. And then we have the first order derivative of the activation function here, which is underived, and we are performing derivatives here. Now, the derivative with respect to AJ is not influencing the weight, and it's therefore influencing only this term. Now we can view this term as the partial derivative with respect to AK, and here we can see that it's a partial derivative with respect to AJ, but in fact we can also swap these two partial derivatives and perform a partial derivative of error with respect to AJ, and that we know what it is because it's simply the delta J, and it's again this term. So what we will end up with here is the first part of the term is unchanged, but the second part we will have here the HAJ times HAJ, so H prime AJ is here squared, and now we will have our previous term here. However, our previous term is multiplied by this sum where we have WK prime, so not the same K, J, and but the same J because the J is related to this AJ, and times the second ordered partial derivative with respect to AK and AK prime. So this AK remained from the previous case, and the AK prime is simply because we performed the partial derivative of the error with respect to AJ again, and that created us this term, and this term here is so this with this new term, and this is the partial derivative from the previous case. So now we have calculated this error with respect to HA, and we know that this error can be then used for the together with the xi squared in order to calculate the second order partial derivative of the error with respect to the weights. So so this term here, which is this term here, just slightly differently written, is now equal to if we consider that the k and k prime is the same, because we want to consider only the diagonal case, then we have the benefit that we can calculate these diagonal terms within the OW computational complexity, and this term is in that case, as it is written in the book, equal to the second order derivative of our activation function in the hidden layer times this term where we have the wkj and the delta k, and then we have the first order derivative of the hidden layer activation function squared, and then we have the wkj squared, and here we have the second order derivative of the error with respect to ak squared, which we already had on the previous slide described what it is. So, and for the linear activation function in the output layer, this will be 1, otherwise it will be yk times 1 minus yk for the, for example, the sigmoid activation function in the output layer. And just to finally rewrite it by expressing it by the error in the output layer, here we have the same thing, just here is the delta k and here is the delta k with respect to the ak. So this is how the approximation of our Hessian matrix can be done by just some diagonal matrix, which is reasonably somewhat close to the Hessian matrix, but admittedly it's not a very good approximation, but it's the computationally least complex approximation. Such a approximation has the advantage that we can also easily invert it. So inversion of such a Hessian matrix approximation will be simply by inverting the or performing the reciprocal of the values along the diagonal to obtain the inverse. The next level approximation of a Hessian matrix after the diagonal approximation is the so-called outer product approximation, which generally would serve as a better approximation than the diagonal approximation. We will explain it on the case of the error defined as sum of square differences. First, let's have a look at how do we obtain the Hessian matrix for this type of error, and that is that we perform the two partial derivatives and generating as first the gradient vector of the error with respect to weights, and then the Hessian matrix of second order derivatives. So the gradient vector can be defined as the derivative of this term, which is squared. So first we perform the outer derivatives, which will be 2 times 1/2 here, and that will cancel itself out, and this term will remain. So this is here, and then the inner derivation, which is the partial derivative of the yn with respect to the weights. And then, so this is the first derivative, and this would be the second order derivative with respect to the weights. Now, this is we can treat this also as a product and perform the partial derivatives of this product here, and that is equal to the sum, and as we have these terms in sum, so we will have, as we are performing the sum
from the derivative, we will have two sum symbols here. And so here we have the underived partial derivative with respect to the weights times the derived first term. So this first term is derived. The second term, we have a transpose here. So we will have a partial derivative of yn with respect to the weights and the same transposed, plus, and here the first part is underived, the second part is derived, and we have the partial derivative, second order partition of the derivative of yn with respect to the w squared. Now we can see that this is like the gradient of the y with respect to the weights twice, where here we have the transpose, and here we simply have this sum here, where in this sum we can see that this term, basically for having the network reasonably functioning well, and that the yn is on average, or the tn average and yn average are the same. Therefore, this sum will equal to 0, or in other words, is distributed by a normal distribution around the zero mean with some precision or variance. So it is a zero mean distribution, this term here, and therefore across all the sample points, and therefore as this is a zero mean, therefore this term will not have a very strong significance in influencing the Hessian matrix, and therefore it can be removed, and the approximation is just from the first term of the Hessian. And therefore we can say that we have a vector Bn, which is a gradient of the yn with respect to the weights, or it's the as the yn equals an, it's also the gradient of the activations in the output layer. And we can see here that the Hessian matrix can be approximated by the outer product of this derivative of yn with respect to the weights. This is also consistent with what we have seen in the case of iterated reweighted least squares. When we were discussing it, we were also calculating the Hessian there, and it turned out that the Hessian is an outer product of the feature vectors, and in fact the gradient of yn is also the feature vector, as the yn is equal to the feature vector calculated from the hidden layer for the and the weights which are associated with the outer layer. So the same feature vector is somehow appearing here again in this approximation. For completeness, also because this has been mentioned shortly in the book, we will discuss the outer product approximation for the logistic sigmoid using the cross entropy error. So the cross entropy error overall error is a sum of these cross entropy terms. So the distribution of t and the distribution of y, where we have the t times ln y plus 1 minus t times ln 1 minus y n are is the cross entropy for one sample n, and if we sum it up, so with the individual terms are individual errors associated with the individual training data samples. However, in the sum, this will form the sum for the entire data set, training set. So we can see that the partial derivative of error with respect to the weights is the sum again of along all the errors associated with the sample with the training data, individual elements of the training data, and here we see that we can represent this partial derivative as the sum of the partial derivative of en with respect to yn times partial derivative of yn with respect to an, and the chain rule is finished with the partial derivative of an with respect to the w. And that is equal to, so the first term, as we have seen it before, is equal to this term, where the second term is in fact equal to this sigmoid here, which will cancel itself out with the denominator, and we will end up in the term where we have just this the difference between the output, the predicted value, and the true value, and the partial derivative of an with respect to the w, and that is again in our case equal to the vector bn. Again, also in this case, it is this partial derivative is essentially telling us how does this pre-activation value, which is a product of the weights with the feature vector, how is this how is it changing with respect to the weights? Well, it's changing according to the associated feature vector values, because it's computed like that, and that is again the bn, which we are using as a term here. And then we have this is the first derivative, and we are actually looking into the second order derivative as well. So we perform the derivative once again, and here we can see that our this term we again now derive as a product, where this term is first derived and the second one is not. So here we have the formation of this outer product, where the partial derivative of the gradient of yn is was in the previous case equal to the gradient of an, and that was the bn vector, but now we just leave it like that, and then as a gradient of yn, we will see just in a moment, and then we have this part here in this the second term, where again we have this term here has a zero mean distribution, and therefore we will approximate it with 0. And therefore only this term is used for the approximating the Hessian, and here we have again the same term, and that is equal to not exactly the bn, but something similar, because we have the yn 1 minus yn, the sigmoid, times this activation, because the gradient of yn with respect to the w, it will be like the yn with respect to the an, which will be the sigmoid, and then the an with respect to the partial derivative of an with respect to the w, which is the bn. So we have another approximation using the outer product, this time for the logistic sigmoid error and the cross entropy error. Sometimes, instead of a Hessian matrix, we are interested in the inverse Hessian matrix. Like, for example, the application for network pruning has been motivated by the inverse Hessian. Similarly, if we want to know a covariance matrix for the Laplace approximation, we are again interested in the inverse Hessian for the knowing the covariance matrix. So let's build on top of the previous approximation of the Hessian through the outer product. This was now in the sum of square differences error. We see that it's built from the sum of these vectors which are associated with our training set. So the vectors Bn and Bn transpose are for each training data point or input point or input vector. We have one such a vector, and its outer product forms as just one term of which in sum constitutes the approximation of the Hessian matrix. But we can also define this buildup as the Hessian matrix n based on n sample points or capital N sample points is equal to Hessian matrix n minus 1 plus the outer product of the last training point b or x capital N, forming as the vector b capital N and its outer product b and bn transpose. So, and we can also reformulate that in a slightly different form as is in the book, where the Hessian L plus 1 is equal to Hessian L plus the outer product BL plus 1, BL plus 1 transpose. And in this case, we can utilize the so-called Woodbury matrix identity, which says that a matrix plus an outer product inverse, so here we are coming to the inverse Hessian, is equal to the matrix inverse minus, and this complicated formula of a ratio between the M inverse times the vector V from this outer product and V transpose M inverse in the numerator and 1 plus V transpose M inverse V. So, and this is equality which we are taking and utilizing for calculation of our inverse Hessian in this progressive calculation of Hessian through the summation of the outer products. So in this case, we can consider this being the HL plus 1 inverse, so it's an inverse of a Hessian, and then we have the previous case before the plus, so like it's here, so we have an HL inverse minus, and we simply put instead of M the HL, and instead of V vector the vector BL plus 1. And the same, of course, for the BL plus 1 transpose representing the vector V transpose. And with this, we obtain the formula how we can calculate the inverse of a Hessian in this form by summing up these terms, outer product terms, and during that during the passes through the network through with all the sample points, we will be able to build up the inverse of the matrix. In order to start with some reasonable matrix, we need to have some initialization of a matrix which is invertible. So therefore, we can take some identity matrix and for the initialization, the initial Hessian matrix, multiplied by some small value of alpha, where that would mean that as we are adding it up to this this value, we will this will result in a inverse of a Hessian plus this value, which is again an approximation of a Hessian, but it's a convenience, and it's relatively small perturbation to the Hessian, which will not change the Hessian matrix dramatically. So after having the approximations of the Hessian matrix with the diagonal approach or with the outer product approach, we have seen how we can use the outer product approximation for calculating the inverse. And now we will confront these approximations with other forms how an Hessian can be calculated. We will see how the numerical approaches can be used for this purpose. So compared to these approximations, we can have a numerical methods to approximate our Hessian matrix. In this case, the approximation is done through the finite differences, where we have here the error term. So we have something similar like we had central differences for the first order derivative, but now we have a second order derivative. Therefore, we will be changing and perturbing not just one weight, but we will be perturbing two weights simultaneously, the weight Ji and the weight WLK. We see that first we add some epsilon value to their position in the weight space, and then we perform the error when we are having, so we subtract that from an error which is calculated from a perturbed weight with these two components, where the epsilon is added and subtracted, again minus the third term, where we have our error term calculated from having the weights perturbed by negative epsilon for the Ji and for positive epsilon for the WLK, and finally the error where both of the epsilons are perturbing the weights in a way that we subtract the epsilon from the weights. So this gives us the this second order derivative of this approximation, numerical approximation, and we also have the we need to scale it by the 4 epsilon squared in order to take into account the area which is defined by the epsilon. Previously, in the central differences, we had there the 2 epsilon, which corresponded to the distance of the range where the from which the gradient has been made. And here we are performing the evaluation of these values, and this is just for one value of the one weight and another weight, where this for in order to calculate the anti-Hessian matrix, we will need to calculate the W square times, because our matrix is W times W size, the capital W. So now we are talking about the complexity. So the complexity of just finding one entry in the Hessian matrix is the complexity of 4 times W, because we need to calculate here 4 times the error, which means we need to pass 4 times through the entire network, and that is reciprocal to the O of W, and we need to do it W squared times. Therefore, because we have the W times W matrix, as I said, and that leads to the overall computational complexity, which is O cubic. So this is for large numbers of weights, million sized or more. This is a prohibitive operation. And please keep in mind that often we need to calculate such a Hessian matrix after each weight update, and therefore this will need to be done every time in each iteration of training, for example. And more efficient Hessian matrix calculation can be done if we take the error calculation from the backpropagation. So here we backpropagate the error and calculate this term only once, and therefore we will and multiply it with these terms here numerically, and we will basically have the same residual error as in the previous case. However, the first case will be calculated with a mix of numerical methods and backpropagation, where one pass is the numerical error method, and the other pass is the backpropagation. And that has an overall computational complexity of OW squared as compared to the cubed one in the previous case. After discussing several approaches for approximating Hessian, either through the diagonal matrix or through the outer product sum or through numerical methods, let's talk about the exact evaluation of Hessian, which is based on backpropagation quantities, and it has also a quadratic complexity. So generally we are interested in finding out our terms second order derivatives of error with respect to weights could be from the same or different layers, could be the same ones, could be different weights. Here we define that the error associated with a certain unit is the partial derivative of error with respect to activation of that unit. And also, this is the first order derivative, and the second order derivatives can be collected in a matrix where we have the entries are the second order derivatives of error with respect to activation K and activation AK prime. So here, therefore, we have the indices K and K prime. Please note that this is different from the Hessian, because here we have the activations through with respect to which we are calculating the partial derivatives and not the weights. So that's the Hessian of the errors with respect to weights. In this case, in order to calculate the exact evaluation, we should distinguish three different cases. Two cases are about when the weights are for calculating the second order derivatives are coming from the same layer, and one case is when they are coming from two different layers. So first case is about the second order derivatives within the or with respect to weights in the output layer. And the second case is that we have the second order derivatives with respect to the hidden layer. And the third case is when we have the second order derivatives with respect to weights, one weight from one layer, output layer, and the other one from the hidden layer. Now, just to also remind us that the error K for the output unit is characterized as yk minus tk, and that's in for the linear activation function with sum of squares error, and the derivative of this error is with respect to, again, activation, maybe a different activation this time, so k prime is equal to, so if the yk and ak are the same, then it's like a y with respect to derivative of y with respect to y, which would be 1, and if it's the ak prime or k and k prime is not the same, then it will be equal to 0, because if this is changing, but this activation doesn't influence this yk, therefore this derivative is 0. And that leads to the fact that these elements of this matrix M, the k prime elements, will be corresponding to the so-called Kronecker delta, where when the k and k prime is equal, then it's 1, and if they are not equal, it's 0. So therefore our matrix M will be in fact an identity matrix. We can keep that in mind. For the sigmoid with a cross entropy error, the situation will be slightly different. We will have here we are calculating the first order partial derivative of error with respect to yk, and that is equal to this term as we have seen it before. And then we have the yk with respect to ak, which is the sigmoid derivative here. And therefore, again, the error is equal to yk minus tk, the same as in the case of the linear activation function and sum of squares. However, the second order derivatives of the yk minus tk, the first order derivative of error with respect to activation, so leading to yk minus tk with respect to the ak prime, is equal to this, which are the entries on of this M matrix at k and k prime location, are equal to the either 0 or yk minus 1 minus yk. So on the diagonal, we will have this derivative of sigmoid terms here, and outside the diagonal, the values, the entries will be 0. So now we will have a look at how do we calculate the evaluation of the Hessian with respect to these three cases, having these quantities of the error delta k and mkk prime in mind. This case is when our weights are coming from the output layer, both of them, and in that case the WKJ, which is the one entry, and we have two of those, is only affecting only the AK, and is affecting, of course, also the resulting error term, but really the activation of the unit K in the output layer. So, and it's affecting it by this sum here, that the AK is equal to sum of WKJ times ZJ, which is the activation from the hidden layer after it has been calculated from this nonlinear activation function. Then the derivative of error with respect to WKJ is equal to the derivative of error with respect to AK, and partial derivative of AK with respect to the weights KJ, and that is, we already know that that is equal to delta K, so the error of the kth unit in the output layer times the ZJ. And therefore, this is the first order derivative, and let's perform the second order derivative here, and we can see that this term, this partial derivative of delta with respect to the K prime and J prime weight is here is an indication that this is in the second layer. Sometimes I put it there, sometimes it's not there. Is equal to now to a sum of or across the K double prime of the second order derivative of the error with respect to AK and the AK double prime times the partial derivative of AK double prime with respect to the WK prime and J prime. Now we can recognize that this term here is actually the term which is our matrix M, because we can see here that it's a partial derivative with respect to the two K's here, and then we are left with this partial derivative of the activation K double prime with respect to the weights, and this one will be only equal to this will be equal to ZJ in K ZJ prime in case the K double prime is equal to K prime, and otherwise it will be 0, because our matrix with Kronecker deltas will everything which is off diagonal will be 0. So out of this entire sum, we will have just one of these terms which is non-zero, and that is exactly when the K prime and K double prime are equal, and in that case, that partial derivative here is equal to the ZJ prime. So with this, we have expressed what is the partial derivative of the error with respect to these weights equal to. Now let's go back and formulate the the entry in the Hessian matrix, which is equal to the partial derivative of the wk prime j prime from the second layer again with respect to this product here, because this is the first order derivative, and now we are basically performing the second order derivative. Now we can perform the second order derivative as the product derivation. So here we have the partial derivative of the error with respect to the weights times zj plus the error times the partial derivative with respect to zj with respect to the weight. However, this is an hidden layer activation outcome, and this is the output layer weight. So this term doesn't depend on this weight, and therefore this term is equal to 0, and only this term is not 0. Now we have already calculated what is this equal to, and that is equal to this mkk prime zj prime and times zj. So the outcome of our for our Hessian matrix entry for the weights which are coming from the output layer is that they are equal to this mkk prime zj prime zj matrix, which means that this will lead to actually only entries on the diagonal, because the values of the diagonal will be equal to 0 through this Kronecker delta based matrix entries. How to calculate the Hessian matrix entries for the weights from the outer layer. Let's have a look at the Hessian matrix entries related to the layer of the hidden layer, and there let's have some basic understanding of or recap of our quantities. So the activations in the hidden layer are governed by the sum of the weights and the input vector entries, and then our activation is based on this reactivation and the activation function in the hidden layer, and the output layer activations are again a weighted sum of our post activations from the hidden layer. And also the wji, which affects all these quantities, is also affecting obviously the quantity of the error. So if we are talking about the first order derivative of the error with respect to the weights ji, meaning from the both from the first layer, the partial derivative is chain rule of the error with respect to the activations k in the output layer, and then the partial derivatives of the activations with respect to the post activations zj, and then the partial derivatives of zj with respect to aj, and finally the partial derivatives of aj with respect to the wji. And now we can put in all these quantities in this sum of these individual entries. So we are dealing with the sum of this so basically the error, how it is influenced by this weight, is then influencing all these quantities, and therefore we can see that for the outer layer, it basically somehow affects all the entries in the outer layer. Therefore, we need to have a sum of the over k of all the outer layer entries, and there the error of the outer or output layer unit is here. So this is the partial derivative of error with respect to the activation that corresponds to this quantity. Here we have the partial derivative of ak with respect to the j. So ak is calculated as a weighted sum of the j's. Therefore, the weights are the result of this partial derivative. Then the partial derivative of the zj with respect to aj is actually the derivative of the activation function in the hidden layer, and then the derivative of aj with respect to wji is here, and the outcome is xi. So here we have this first order derivative nicely represented, and some of these quantities, like these two, we can take out of the sum because they are not dependent on the k, and we have here only these two entities dependent on k, the weights associated with the outer output layer, and the errors associated with the output layer. And we can also reformulate this as because this part here with the derivative is basically the error in the hidden layer, delta j, so it is delta j times xi. Now we have performed the first order derivative, but we want to perform the second order derivative here for the weights ji from the first layer and the j prime I prime from the first layer. So now we can already formulate it as so we have here the first order derivative outcome, and so we take the xi and the delta j are replacing this first order derivative, and we have now the first order derivative of the delta j with respect to weights j prime I prime, and that is multiplied with the xi because that is not affected by the weight. So it comes as a constant multiplier in front. Now, so we need to now perform the derivative of this, which in itself are these terms, and we can see that it's a product of this term with this sum term here, and we also perform the derivative as a product. So here is the derived first term, and the sum is underived, and the second term is not derived, and the sum is derived. So this sum is derived with this partial derivative with respect to j prime I prime weight. So that it leads to the outcome that here we have the second derivative of this activation function at the unit j, and then we have this previous this form here is of course as a result of the chain rule. So we have this first term, and then outer derivation, and then the inner derivation, which is the partial derivative of aj with respect to this weight. And then we have the sum, which is underived, and then we have the second part of this term where we are again performing the partial derivative of the error with respect to this weight, because this weight is in fact not influenced by this weight in the same layer. And that further on can be reformulated here into, this is still the second order derivative of the activation function, and here we have the so-called Kronecker delta, which is either 0 or it's 1. Actually, for the purpose of in case the j and j prime is equal to the same value, then it's the result of this partial derivative is xi prime, otherwise it is 0. So this aj activation in the first in the hidden layer is with respect to the weight associated with the hidden layer is only related if the j, this j here, connects to this aj and this j, and it's only then when the j prime and j is the same, are equal. So that's why if they are equal, then this partial derivative will be equal to xi prime because it connects to the I prime here, and otherwise it will be 0 because it is not influencing the weight our aj. And and the rest of the sum here remains unchanged. And then in the second term, we will be replacing our partial derivative of the error with respect to the j prime I prime with with a formula representing the second order partial derivative with respect to the activations, because we can represent this this delta as the partial derivative with respect to activation, and then swap this and the activation will be with respect to ak, and then we have the partial derivatives with respect to wj prime I prime, which goes from ak double prime and then ak double prime partial derivative with respect to j prime, and the partial derivative of zj prime with respect to the weight j prime I prime. So we expand here this partial derivative of the error with respect to the activation with respect to the weight into this with respect to the weight in the hidden layer into this long form, and represent the error here as the partial derivative of error with respect to ak. Now that we have that, we further can see that, recognize that here we have again this matrix M, and this matrix M is the first term. The second term is the WK double prime J prime, so it's the partial derivative of this activation with respect to in the output layer with respect to the post activation in the hidden layer, and what is connecting them is the WK double prime J prime, and then from the second layer of weights, and then we have the partial derivative with respect to the z here, of partial derivative of the z with respect to the weights, and that leads to the partial derivative of the or derivative of the activation function, and then the derivative of the activation with respect to the weights, which is the xi prime in this case. So, and the final formulation is that we can recognize here that we have here xi and prime, and here we have also xi prime, so we can take it, and we have here this kind of almost a xi squared term, which we had before in the diagonal approximation, but here they are not necessarily the same xi entries in the input vector. And then we have this term involving the Kronecker delta, double second derivative of the activation function in the hidden layer, and then the weights and our error from the output layer. Then we have the first order derivative of aj and aj prime, which we took out from this term, and then we have the formulation of wkj and wk double prime j prime, and our matrix diagonal matrix mkk prime. So while this represents here a double sum, it will, for the cases we have discussed, for the linear activation function in the output layer with the sum of square differences, or the sigmoid with the cross entropy error, this will be a diagonal matrix, which means that the non-zero entries are only in the with the k and k double prime are equal. Otherwise, this term will be zero, as this term as a contribution to the sum will be zero, and the while this sum will not be zero overall, because it will be summing up only those terms where the k and k double prime are the same value. And now, after we have seen for both the outer layer and the hidden layer our outcome of what are the Hessian matrix entries, we will have a look at the mixed layer. To deal with for exact calculation of the Hessian matrix is the case where we have mixed partials for weights coming from the two different layers, one from the hidden layer and one from the outer layer. They are index 1 and 2 in the these two layers. So first, let's perform the first order derivative, partial derivative of the error with respect to the weights in the first layer, and we had that already, and we have the result readily available, that it is xi times the h prime ha, which is the activation function derivative, times the sum of the error in the units of the outer layer times the weights from the outer layer. Now here is a sum, because we can see that this weight here is as in a fully connected network will be then influencing all the k units in the outer layer, and therefore its partial derivative with respect to this is involving all the errors which are which are in the outer output units. But also we know that this term here with the derivative of the activation function and the sum is in fact the delta j, so it forms the error of the hidden units. Now this is the first order derivative, and the second order derivative which we need to perform is with respect to the weight from the output layer, k prime j prime, and therefore we perform the derivative of the so this two terms here are not affected by this weight. They are not dependent on this weight. This is the input vector entry, and this is the derivative of the activation function. But what will be affected by this partial derivative are the elements in the sum, and we treat them as the product derivation. So first, this delta k is underived, and the wk is partial derivative with respect to wkj is this partial derivative here, and then the plus the weight is not derived, but the partial derivative of delta k with respect to this weight is the derivative here. Now, if we observe this, we can see that these two are not really affecting each other unless the k is equal to k prime and j is equal to j prime. So these two weights are the same, and in that case, this is equal to 1. This partial derivative, and therefore this will be equal to the this term will equal to the delta k. For all other cases where the k or j are not equal to k prime or j prime, this will be equal to 0, and therefore this term will be 0. And in the second part, we will see that this partial derivative, what is it equal to? This is the partial derivative from the which we already have calculated for the second layer, and that one is equal to the m k prime times zj prime. So that's this term, which is then multiplied by this term here. So the total outcome of this derivation will be that we have this multiplier before the sum, and then these two summed terms in the sum here, and this can be reformulated in the way that we can take this term out of the sum, in fact also this z, and we have this final formula in the as an outcome for the entries of the Hessian matrix from the mixed weights, from the one from the first layer and another one from the second layer. And with this, we have completed the calculation of all these entries in the Hessian matrix, which is an exact calculation, and its computational complexity is W squared, because we just need to calculate these quantities, and then we just have a formula for calculating these entries for each element in the Hessian matrix. Summary for this exact calculation, we should proceed as follows. We first calculate the errors in the output units for each output unit. Then we calculate the second order derivatives of the errors with respect to the activations, and for chosen nonlinearity, for meaning the activation function, and the loss, meaning the error function. And once we have these, we compute for each hidden unit j, we compute the zj, the partial derivative of the aj, and the second derivative of the activation function at the unit j, and then we assemble these second derivatives for each pair of weights in each block using the formulas which we have devised on the previous slides.
As the last topic, we will discuss fast multiplication by the Hessian. The key idea is that while we need Hessian for various types of computations, sometimes we just need it for multiplying it with some kind of a vector, like with a vector v, for example, here. And this multiplication can be actually reformulated into something where we never really compute the Hessian matrix H, but we compute directly the product of this vector V with the Hessian, which in itself will become an vector as well. So, such a fast multiplication scheme by the Hessian is of OW complexity, where the capital W is the number of weights. We can see here the key logic where we can see that the multiplication of a row vector V transpose with Hessian can be understood as the multiplication of the row vector with the double gradient of the error with respect to W. And this can also be understood as a directional derivative in the direction of the V of the gradient of the error with respect to W. So the idea is that we calculate the gradient of the error instead and use a differential operator V transpose nabla defined as a function R such that R of W is equal to V. So let's now try to understand what this operator, this different directional differential operator actually means. It means essentially that, which now is replaced by this function R, it means it basically answers the question, if we add to the vector W a small, the vector V, how much does the V change in the direction, how much does the sum of these two vectors change in the direction of V? And the answer is, it changes exactly by the V which has been added. So that's the result of this equation. And therefore, this function always evaluates by an addition of V, what is the change of the function in the direction of V. So it's a differential operator, directional differential operator. The operator measures how do all activations, so not only the weight, but then the results of mathematical operations on the weights, activations and errors change if we move the parameters W in the direction of V. So in that case, if we look at our activations AJ, these activations are an product and accumulate or sum of the individual input components weighted by the weights Wji. And then for the purpose of understanding this directional differential operator, we add to this Wji the corresponding component Vji to this and replace this weight by this new weight, and we can see that it is equal to the Aj plus Raj, and the
Raj is equal to the Vji times Xi. This means that if we added the the to the weights W, the vector V, the change of the activations Aj will change uh, by the product with the Vji and the sum of that. So that's the this is not the new weight or new activation. This is just the change with respect to the old activation without adding the direction v to the vector w. And we can follow the same logic of this uh, differential operator represented as the function r further to the next quantities. The next after in the two-layer network where we have one hidden layer with a nonlinear activation, we already know how to calculate this pre-activation, and now we will see how the post-activation quantity C is calculated. It is evaluated as the age of Aj. So this is this generally nonlinear activation function, and therefore the Rzj is equal to the derivative of this, but this term, but the directional derivative, and therefore we are performing derivatives of the both quantities here, where one is the quantity of the change of the z with respect to the aj, which is the inside function, and then actually the outside function, and then we have the Raj, which is the directional derivative of the pre-activation quantity itself, and that is equal to the h derived times the Raj. The next quantity along our feed-forward network propagation is the output layer, where we calculate for each output unit yk, again a dot product of the post activations with the weights k. By multiplying the individual components and summing them up. Now, for the new variable ryk, so we can treat these activations, post-activations, and outputs in some sense after applying this function r as new variables, and this new variable of the derivative, this directional derivative of the yk in the direction v is now we can see that there are two quantities here where which both are subject of this directional derivative, because both the w and also the c are changing by the change of this addition of the vector v. Therefore, we are now treating this derivation as a product derivation, and therefore first we have to derive in this sum the first component is underived, the directional derivative of zj, we know it's now rzj, and now we have the first component derived in the second a part of the sum, which we set the operator R on W is actually V, and the second term is underived. Now, furthermore, we proceed to the errors along the now back propagation. We evaluate the errors, which is in the all output units, which is yk minus tk, and the R of delta k is therefore it's just R of yk minus tk, where the R of tk is 0 and R of yk is yk. So therefore R of delta k is equal to yk. Then we have the delta j, the errors backpropagated in the hidden layer, and we have the known formula for that, where we have the h prime aj is the first derivative of the nonlinear activation function times the sum or the dot product of the delta k with the weights k. So this is the most lengthy directional derivative, but we will just derive it in the way as we did the derivatives before. So as this term contains a quantity which is subject to this directional derivative, and also this term, in fact, both of them. Therefore, we will perform the derivative of this as first one product and then as the second product. Therefore, we see that we first perform out of this derivation. First, the directional derivation of the first term of this derivative of the nonlinear activation function in the hidden layer, and times the underived second term. And then we perform the derivative of the underived first term and the derivative of the second term. And here is the result of the first derivative, where we have the arch of the activation function is the outer derivation and the inner derivation of the aj, and then this is underived. And then here we can see that this product again has two quantities which are subject of the directional derivative differential operator, and therefore we first perform the, so this is underived, but this in the sum, the first term is derived and the second is underived, plus the last term where the first term in the sum is underived, and the delta k quantity is derived with respect to the this directional derivative and represented by this function r. So now we have all the quantities when we've been calculating from the backpropagation for the gradient, but we applied this differential operator. So we applied the differential operator of directional derivative along the direction of v vector v directly on the quantities which are used for calculating the gradient, and now we just have to calculate the gradient of the error with respect to the weights. So for the outer layer weights partial derivatives, the product is delta k times ck, where we have both of these quantities are subject of this directional derivative. Therefore, we use a simple product rule, where the r delta k times ck plus delta k times RZJ is the result of this directional um, differential operator R on this gradient, and we can then replace all these directional derivative quantities by their actual values, like that will be ryk, then yk is equal to furthermore this term, and then there the rzj is equal to the a term which we had on the previous slide, and so on. So we just put in all these values. And for the second part of the gradient, or the directionally derived gradient with this directional differential operator, we have the original gradient terms are delta j times xi. The xi is here not acting as something which is changed by the change by adding the vector v to the vector w, because it is before any it is an input, and therefore in this directional derivative it just acts as a scalar multiplier, and we perform this derivative of delta j, of which we also have calculated what it exactly is, and by putting in recurrently these quantities back, we can then calculate what is the final entries for both of the gradient components coming from the weights in the outer layer and in the hidden layer. And those resulting vector is already the vector which is multiplied with the Hessian matrix. So with this, we have a very highly efficient Hessian matrix vector product calculation by realizing these identities from a differential calculus. Let us now go back to how we started discussing the neural networks, where at the beginning, where we said that our feature basis functions can be represented as the linear combination of weights and inputs, and sum and as an argument to a nonlinear activation function. And therefore, our hidden layer units are representing us these basis functions, and that leads to the link to our previous discussion on maximum likelihood estimation, and how can we possibly avoid aspects like an overfitting or too rough approximation, where one of the solutions was the regularization. So imagine that we have just a differing number of hidden layer units with an activation function, which is the 10H, and it's just a varying number of hidden layer units. So in this figure here on the bottom, you can see that we have our sinusoid dataset, which we were dealing with all along throughout this course, and we see that it has been sampled by several samples, forming us the training set of inputs and corresponding output values. Now, we have been imagined that we have now a this leads to a very simple neural network architecture where there is just one input as a scalar and one output also as a scalar in this regression problem. And in our network, the M defines the number of hidden layer units. And therefore, in this case, this is just one, and we can see that when we are performing training, our training leads to the fact that we have our function looks pretty much like the 10H function, except that it is horizontally mirrored. So therefore, we see that this is the hidden layer of one hidden layer is not enough to well represent our sine function in the neural network type of realization of the regression. If we look in the middle picture, we see that if we increase the number of hidden layers to 3, then we can effectively train the neural network to represent our sine function actually pretty well. And then if we further increase now the number of hidden layers, we see that for 10 hidden layers, we are overfitting our function to the noise. So this is a much worse result as the case when we have just 3 hidden layers. So it matches very well with the standard case when we are dealing with then different model complexity. And the model is more complex when it has more hidden layer units and possibly can lead to this overfitting problem. So one possibility, again, as it was before for in case of the linear models, we can also incorporate a regularizer into our error function, and the regularizer could have the form like it had before, where we had the regularizer basically penalizing the large weights. So we wanted to have this square root of or dot product of the weight vector with itself to be as small as possible, and the contribution of this regularizer was controlled by this parameter lambda here. So we could use the same concept, and we can also see this as it was a result before as the corresponding this regularization to a prior which has a zero mean. Now, finally, let's have a look at the experiment performed here with various model complexity, so different sizes of the hidden numbers of hidden layer units, and we can see that there have been that here we can see the error, and this error has a distribution. And we have here several runs or initializations of our iterative approach to reach the certain weight, and here we can see therefore that there is a large error associated, which we have one hidden layer, but then we have several of these cases until let's say 7, or where we have a relatively small error all along, but for some initialization the error is slightly larger. with increasing the complexity, we see that there is also an increasing amount of large errors associated with some initializations, which shows us that this nonlinearity in the neural networks, so that we do not have a single minimum, can lead to a local minimum, which can exhibit rather large errors. For a lower complexity models, we will also have less local minima overall, and therefore we will overall have a higher chance of a relatively low error performance. So let's consider now this case of the regularizer, and one aspect to consider for the regularizer is how it behaves when we just simply perform a linear transformation on our input or on our weights. So imagine that our network is pretty much defined in this standard two-layer network way, where we have some nonlinear activation function, which is receiving as an input the activation, where the input is weighted by the weights plus the bias, and then the output is calculated from this post-activation and again weighted by the weights and plus the bias. If we have this type of error function with the regularization here, we can see that in order, if we perform some linear transformation on the input, so the input is no longer xi, but this xi with the accent of the wave, and this in order to achieve the same values for the y, we can scale these weights associated with the hidden layer and also the bias, and the overall sum in here will remain the same. We can have a look at it. This, if multiplies with this, will the a will cancel itself out, only that the b will accumulate this b divided by a for each wi for all the weights, and therefore our bias vector will need to subtract it off, so that we have overall the same argument for our nonlinear activation function. So these weights and biases would need to be adjusted to cope with this linear transformation. Similarly, if we rescale the output, so the output is now somehow scaled, and there is additional shift added to it, we can imagine that that can be realized also by changing the weights, scaling the weight, and also adding some factors to our bias term. And that is, in fact, changing these weights means that the weights will be changed here as well, while in this case we will, when we rescale the input, the input will be rescaled, the output will be the same. However, the regularization will act in a different way. It might be, if we have a scaling factor a, let's say, higher than 1, this regularization might be more aggressive, or less aggressive if we and it will not be the same. So this regularization is not consistent with respect to linear transformations. Rescaling leads to different weight vector, which leads to different regularization penalty depending on the transformation parameters. So therefore, just a standard regularization would not be very fortunate to incorporate these two possibilities of linear transformations applied on the input or on the output. Instead, we can consider some other regularization which will be able to have this property of being scale and shift invariant, and that also will lead to a consistent Gaussian prior. So how does such a regularizer might look like? We can see that such a regularizer can look like in the following way. Instead of just having the one lambda and multiplied with the dot product of the weight vector with itself, we can see that we have now here a sum of two terms where one sum is associated with the hidden layer units, and where we perform the square of the weights for all the hidden units associated, and then we have a separate lambda 1 here, and for the output units and the weights associated with the output units, we perform a separate square term and summed up, and it is associated with another lambda 2 hyperparameter. And if we are performing these different scaling properties, like the scaling the input with A, then if we remap our lambda 1 to square root A lambda 1, then we will have a consistent regularization. In case we are scaling the output, we will have then the lambda 2 will be remapped onto 1 divided by square root of c times lambda 2, and that will lead again to the equivalent regularization as if we would not have the scaling aspects here. In this particular case, we were not including the biases, so we only perform in the regularization with the weights. If we now turn this regularizer into a prior, a Gaussian prior, then we can represent it as the prior with these two parameters, which is proportional to the exponential term, where we have one, where the alpha 1 is forming us the precision of one exponential term, and lambda 2 is forming us the precision of another exponential term. And we can see that in order to calculate this probability, we will need to perform calculate also the scaling factor based on this exponent, which we can do on one hand. However, as we didn't include the biases in this case here, the weight 0 associated with the hidden layer or the weight 0 with the outer layer, the biases are not included here. Therefore, this will not be a properly scaled probability distribution, and that means that this prior will be improper. If we would like to have a proper bias, we would need to include the biases in our prior, and that can be done, for example, by including the biases separately with a separate precision of this probability distribution term here. So, and as such, then we can perform the normalization of this exponential term so that the overall probability distribution is sums to 1, and then the prior will be proper. However, in that case, we will lose the shift invariance property, and we will only have the scale invariance property. More generally, this term can be represented in a way where we have a sum of various elements coming from various network layers, for example, plus the biases. This can be seen in the example here, where there is the probability of the W as a prior is proportional, and we can see here a scaling factor, so the -1/2 is here, and then we have the scaling factor alpha k. Before we had like alpha 1, alpha 2, and alpha beta then, which were serving as the precisions of these individual probability distribution components, which are then product and summed up, multiplied with each other to form the final prior. And then in each we just have the square of the weights which belong to a certain weight layer, or they are biases. Now, for a case when we have a two-layer network and we have hyperparameters about the prior distribution with a single input and single output, so like we had in regression, and we have 12 hidden layers with 10H activation functions. So these 12 hidden layers can be also understood in the linear models. We had 12 basis functions, so we have 12 hidden layers with the 10H. Then if we perform an analysis, how are these individual functions, the hyperparameters alpha, changing the shape or scale of our regression problem can be seen here. So we can see we have a data set of simply a training set of inputs on the interval -1 to 1, and then we have corresponding outputs here on the real axis for the yk. So this is a single input and single output, and we were training this neural network regression problem several times. So each line represents a completely different training, and we can see that based on the different nonlinear behavior of the neural network, where we have several local minima, we can see that our result of the regression can have varying outcomes of and predict a different function. Now, if we are performing the change in one of these parameters, like the alpha 2 for weights, so not the bias term but the weights term, we can see that the weights are now changing the prediction of the outcome. So we have now suddenly the interval is from -60 to +40 if we change the alpha 2 to 10. If we are changing the alpha 1 to 1000, and so for the weights, and the bias is 100, we can see how does the prediction drastically change our prediction of the function when it's trained for different and in different separate models. now if we keep the same alpha hyperparameter for the weights in the hidden layer and just increase the bias, we can see that the bias is scaling this function horizontally. So what was here previously shrunk is now becoming much more stretched. If we are performing a similar operation on the alpha 2 weights, we will observe that there are vertical offsets then to be observed and changed there. So it's this is somehow associated with horizontal offsets associated with the input, and the biases for the bias associated hyperparameter for the layer 2 will be associated with changes in the vertical offsets. It is very interesting to study the aspect of regularization and at the first glance a different aspect, which is called early stopping. Imagine that we are training neural network and we are performing the training, and during the training we can see how our error is gradually decreasing for the training set. So every time our weight vector is being adjusted, we observe that we have a slightly different and lower error. If on the training set, if we have a separate set which is not used in the training, but we are evaluating the error on it, we can also observe a similar behavior. The error will be generally higher than for the training set, but the shape of the error will look quite similar. So we will observe during the training in the initial phase like the error is decreasing, and then at some point it will reach a minimum and the error will start to be increasing afterwards. So we can observe that after almost 30 iterations, the weight vector is trained to such a degree that for an independent data set, it is having the lowest error. And after further training, while the training data associated error is still decreasing, on the validation set it will be increasing. So that has actually an indication that we are now starting to overfit the training data with our weights. So, and therefore, it might be a good idea to stop the training when the validation data achieves the lowest error. So what does this have to do with the regularization? Well, if you are observing and how your weight is changing during the training, you can see that we have here just a very trivial plot of two weights, and our weight, where here we have the maximum likelihood estimation of the weight, and we can see that our weight is first changing in the vertical direction, then it starts to align with the isocontours of our errors, which would be observable by the properties of the Hessian matrix here, and we can see that it will lead to this the maximum likelihood estimation, which will then, for a neural network with sufficient amount of hidden layer units, will clearly lead to an overfitting. So here, this weight with the axon of the wave is now indicating that we have performed an early stop. And this early stop, we can see that it's somehow closer to the zero, to the origin in the weight space, meaning that it somehow has been regularized. It's closer to the zero than the actual final WML, which we would be achieving by long training time until we perform, until we suffer from overfitting. So it can be somehow explained qualitatively that during the training we are performing and the training has some effective degrees of freedom, which is starting very small and gradually is increasing. So at the beginning of the training, the model is rather simple and it starts to be more and more complicated over the training. So the effective complexity of model is increasing throughout the training. And the early stopping might limit this at effective network complexity, which in these terms leads to a regularization, to an equivalent effect as regularization. In fact, it can be quantified to such a degree that if we have the eta as a learning rate and tau as the number of iterations in the as parameters in the sequential stochastic gradient descent, the product of tau and eta corresponds to the reciprocal of the lambda hyperparameter, which is the hyperparameter controlling the regularization. So the regularization, a special form of a regularization is the early stopping, where we are noticing that the error in the training set is starting to increase. In pattern recognition, we would often like to have the recognition, classification, or regression invariant to certain shift, scale, rotation, or warping. So somehow a transformation invariant. Imagine that we see a particular pattern, let's say a letter K by a camera, and if this letter K is slightly turned in one or the other direction or slightly shifted from a center of the image, that should not affect the capability of recognizing that letter K. So this can be achieved in a way that we have a training set that includes all these invariances. Imagine for the letter K, we would need to have to store all the positions, all the rotations, all the scales, so magnifications of the letter that we would like to be able to recognize the letter K in the training set, so that the error can tune the weights by means of the back propagation and a sequential gradient descent, and in such a case our training set will incorporate these rotational or translational or generally transformational invariants. But this is not the only way how we can achieve it. It has a certain disadvantages. The training set, or to obtain a training set, is already usually a complex task because it involves a lot of data, and now involving or including all these transformations will explode the size of the training set. Therefore, we have several options what we could do. One option is that we perform the so-called data augmentation. So we have our training set, and there are not all the transformations, but we can, before a certain training pattern is becoming used in one training iteration, we can perform some transformation against which the recognition should be invariant. And this is called data augmentation, where we reuse the current data set and we transform it before we use it in the training process. The second approach, which we will be just talking in a moment, takes the data set as it is. It doesn't change it, but it includes a regularization term that penalizes changes in the model in case of transformation. So it will, if there is a transformation which we should be invariant against, this regularizer will have very low value. And if there are other transformations which we should not be invariant against, then this regularizer will have high value. Then another approach could be that we handle all the pre-processing handle all the invariants in the pre-processing stage. So, for example, if we want to have the sizes of the heads roughly equal to recognize faces or facial features, then we can crop to the head and have the data of a face at the same resolution for the entire training set. Another approach could be that we build the invariants into the neural network structure. And that is an example, for example, of convolutional neural networks, where the scale invariance, for example, or translational invariance is a property of such a neural network architecture. We will be talking about that a little bit in a moment. Here we have one case of example of a data augmentation. So you can imagine we have as an example a number 6, and what we could do is to slightly change the appearance of this number, and that could be done in the following way. We perform first just create a random vector field where we will use this vector field for displacing certain values within the image. So, and then this random vector field can be smoothed by a smoothing kernel of various size. Like, for example, in this case, this is of the size 0.01, 30, and 60. So here we have a very smooth vector field. Here it is also reasonably smooth, but here it is very random. And we can therefore generate 3 different appearances of our letter 6, where we can see that here nothing really changed. It's kind of more noisy, while in the other cases we can observe that the number 6 has been, for example, somewhat rotated. So this is an example of how we can augment our training set with where we have already known class, and we are just slightly changing the appearance. At this point, let's talk about the second approach, where we use regularization in order to allow for a certain transformational invariance. So the idea here is that we make the model invariant to transformation through regularization, and we can do it if we have some continuous transformations, like, for example, a shift could be a continuous transformation, or, for example, a rotation could be a continuous transformation. A mirroring would not be a continuous transformation in such a case. So we have an input vector, and then we can apply the transformation, a continuous transformation, changes vector xn such that it sweeps a manifold in a d-dimensional input space. Imagine that we have, like for example here, we have one input point xn, which is having two components x1 and x2, and we apply our transformation. This transformation is just governed by one parameter, like for example, it could be a rotational angle in some cases, not in this case, however. And now we can apply this transformation, and we can see that this point xn, by applying the transformation, sweeps some manifold. And as it is just a single parameter, it sweeps a one-dimensional manifold, one-dimensional manifold M or curve in this case two-dimensional space. So for this, we can formalize this kind of transformation by denoting the resulting vector after applying the transformation as the vector S, which takes as input the input vector xn and the transformational parameter, and then performs the transformation according to this parameter. So for example, if the transformation is on x with 0 as a parameter, the outcome of this transformation or this vector, transform vector, will be untransformed vector x. Therefore, we can define a tangent curve to the curve, in this case, tangent to the curve M to the manifold M. This is in the particular case where we have this one-dimensional curve because we have just a single scalar as a parameter. So that will lead to a tangent line, which is obtained by partial derivatives of our transformed vector, input vector, with respect to this transformational parameter. And for each input point, we can therefore have this kind of partial derivative where we have this transformed vector with respect to the xi, and the xi is very small or infinitely small. So we can say equal to 0 at the partial derivative case. So then we will have this tangent, and this tangent will help us to essentially obtain the next possible transformed point xn in the direction of the tangent. So if we are looking at the changes of the output y, the y will generally change if we change the input by the transformation. The y will change. So we can express a partial derivative of this change of output with respect to the transformational parameter. That is equal to the sum over all the input space dimensions where we are performing the partial derivative of the output with respect to the input vector component, and will be multiplied by the partial derivative of the input with respect to this parameter xi. And in fact, this leads to the sum of the Jacobian. So this is, please note that this is actually the Jacobian element entry of the Jacobian matrix, and this is the element in the vector tau. So we already know how we can compute the vector tau in practical implementations. This could be, for example, done by the finite differences, for example, between the slightly transformed vector xn after transformation, or in other ways. And the Jacobian we can calculate through the backpropagation, and this term will basically characterize our transformation. And now at this point what we could do is to extend the error term by the regularization that encourages the local invariance under this transformation. So the error term is extended by by omega, where the omega is in fact the square of this change of y with respect to this rotational parameter psi. So as long as we are we perform just this transformation, the actual regularizer will be invariant with respect to this type of transformation. So we can see that after we replace this partial derivative with the actual sum of the components of the Jacobian with the tangent vector components, we have here this squared term, which will serve as the regularizer in our error term. In case we have L parameters, the M manifold becomes an L manifold, and the regularizer will be sum of all these individual parameters. So we will have 3 times such a squared sum is our regularizer added to our error in case the L is equal to 3. And several transformations can be regularized with separate terms, like separate omega terms, and what we will achieve is that we will become locally invariant to the combination of these transformations. The tangent propagation can be seen in the context of data augmentation or expanded training set in the following figure. We can see that in the figure A, we have the original representation of the letter 6 from our training set, and then we are applying a tangent vector tau to this instance from the training set by slightly changing and rotating this letter. So the parameter psi is in this case a rotation. Now we can see that some colors have changed here in the B. One is yellow and one is blue. We can regard this as blue is positive values and the blue and the yellow is negative values. And simply if we look at all these vectors, all the vector of inputs which we have here, we can simply say that this is the changed input. In fact, this is the tangent vector tau. So it measures how does the change is performed from the untransformed object, if we add the vector tau, to a transformed object. In the C, we have the outcome of the adding the portion of the vector tau to our input vector, and here we can see the result. So this is a slightly transformed letter, a slightly we can say it's rotated by a few degrees. And then in the last image shows how does the actual data set entry for the rotation by minus 15 degrees look like. And we can see that they are quite corresponding to each other. So here we can perform this by either having this letter already in the training set, or we can have the data augmentation process performing, giving us this representation of the number 6, or we have it implicitly represented by this tangent propagation. Now, we will be talking about how does the tangent propagation relate to this data augmentation, and we will see that they are very closely related, as these drawings here already indicate. So training with transform data is related to tangent propagation. Imagine that we have we have a continuous case of our training set, and in fact we have an infinite training set of x input vectors and the corresponding target values t, and we have our trained regression here. Regression results in the function y, which is we are here by this error, we are measuring the sum of square differences of y, and it's distance from the square distance from the t. So this is an untransformed infinite training set. Please note that in this integral we are including also for the random variables of x and t the corresponding probabilities, so p of x and p of t with respect to x, so that we have it consistent with what how we have been defining the error functions back in chapter 1. Now we can now include the transformation of the training set into this error by simply adding the probability of the transformation parameter, and then we also have here the transformed x, which will then be the parameter of y. And we are measuring the error with respect to this. So this now function is a new error function which includes the transformation of the infinite training set, and these transformations themselves are infinite as well, as we are dealing with the continuous case. Now we have the probability of our rotation parameter or a single scalar parameter of our transformation psi is following a normal distribution with a around the zero mean, and it has the some small variance, so the psi doesn't change too much our input vector, or the transformation doesn't change the input vector too much. It is the actual parameter psi is somehow with the values with a high likelihood around 0. In such a case, we can formulate for our transformed input vector psi a Taylor expansion series to the second order derivatives by first having the untransformed value. So we have here the psi is equal to 0, and then we are looking for how does this the transformation change the input vector upon the transformation when the psi is somehow close to 0. So we can see here, as this is in fact the delta represents the delta to the input vector, then we have psi here times the first order derivative. Then we have the here the second order derivative with psi squared divided by 2, and the second order derivative at the value psi equals 0, and then we have some residual error associated with the psi powered by 3 or higher. So we can represent our Taylor expansion series as the x, which is coming from this untransformed state, because the transformation parameter is 0, and then we have here, this is in fact our tangent tau, because we have here this partial derivative with respect to psi, and then which is the vector we just have seen on the previous image represented. And then we have the second order derivative, and we can say that this multiplier stays here, and then the second order derivative is simply the first order derivative of the vector tau. Now we can regard these values here as something which is delta x, and the delta x is the argument for the y function, which we also performed the Taylor expansion series of, where we have the delta x becomes the part around which is the multiplier of the first order derivative, and the delta x square term will be the associated with the second order derivative. So we have here now that the y at the small offset from our x is equal to yx plus the gradient of y, so vector of the partial derivatives of y with respect to the x, and then we have the times the delta x, this delta here, and then we have the second order derivative, which is in the multivariate form, having this square term delta x transpose, and at the end times delta x, and we have the Hessian matrix here in the with which these two vectors are multiplied. Now we can put this into the we can further simplify this. So this is now here the x plus delta x is in fact is this term. So we can put it here, and it is equal to the yx. And now we can, instead of the delta x, put in the actual values. So it will be the psi tau times the gradient of yx. So here we have this psi tau gradient of yx, but then we have also this term, which is also multiplied with the gradient of yx, and that we can see here, but it's already associated with psi squared divided by 2, and the tau prime is here. So we can see that this term, this multiplication, has been already put here, and then we have the last part is this term here, which now, if we put the delta x for the delta x, the corresponding values, we will find out that it is the for this part it is the tau transpose, and then create the Hessian matrix and tau, so that is for this first term, and then we have twice the scalar of psi here, which is then multiplied with this 1/2, and this is the term here, and the rest, in fact, will be the further more the terms which are associated with higher polynomial degrees of psi, and that is all represented by this residual error here. So we have expressed now our value y with respect to this transformation. And now, as we have that, we can put it back into the error term which we have formulated before. So just before that, we have this error term here, but we want to express the square term with sum of square differences. So if we now have this term minus t, we can see that this is the yx minus t, and then all the other values which we have seen from this devising the formula. So we have the psi, tau transpose, and the gradient of y, and then we have the terms which are associated with the psi squared term, and as we have seen before, with this gradient of the y is associated with I prime, and then we have this square term associated with the Hessian matrix. And now we even have to perform square of this delta psi in order to find the term which is in the error term. So now we regard the yx minus t as kind of like imagine that it is an a, and this is b, and then we have the a plus b squared, which will be equal to a squared plus 2ab plus b squared. So that's what we do here. Now we have a squared is this term here, and then we have 2ab, so 2, and then a is this term, and then b is simply this term here. And then we have plus b squared. So we have simply this term here squared. And that is our delta psi squared here, which leads to further more psi values which are of a higher degree than the quadratic. So therefore, we can only pick all the terms which are where the psi is of the first degree or the second order polynomial degree, and we will end up with the term, this square term here, plus this linear term here, plus the quadratic term here. So we have picked only those values which are associated with the quadratic degree, and we have this term here, which is the square of the gradient of and tau. Now let's go back to our error, which includes the transformation, and that error now is performing, so we can now replace this one term where there was the square term by this entire formula, by this term here. So we do it, and we can see that it is a triple integral where we have now the first term, and then we have the term with the psi linear and psi quadratic, and then we have the rest of the formula, which includes the probabilities pt given x and px and the probability of our rotational or otherwise transformational parameter. So, and that is equal to, and we can take out this probability which is associated with these these terms here, and this is in fact so what we can do is we can separate this into several terms. If we have this part of the sum here, the xi is not part of this expression at all. Therefore, we can represent this sum as a double integral, not triple integral, and remove the probability of xi altogether, because it will integrate to 1 anyways. And then we have this term here, which in fact is this untransformed error, which we started with of the infinite training set. And so this is the regular error without this axon of the wave, in fact. And then we have this term here, where this is the linear term, and from this linear term we have taken out the probability of xi and multiplied with xi, and that gave us in fact as in an integral the expectation of xi. And then we have the next last term associated with the xi squared, where we have this term associated with the xi squared. However, we have again done the same. We have taken out the xi squared and the probability of xi, and that corresponds to the expectation of the xi squared. Now, as we can see here, we have, while this is super all complicated, this one double integral is simply our error, which we see here. The second term here is multiplied with the expectation of xi. What is the expectation of xi? As the xi is the random variable associated with the mean 0, so 0 mean expectation will be therefore 0, and therefore this whole term will be 0. So we will be left with this term, which we can call for now as it is this expectation of xi squared. We can call it lambda, and we can call the rest the double integral as the capital omega. We can also transform this double integral to a single integral by integrating with respect to dt, as we can see that t is only appearing in this one term here, and in fact this is therefore an expectation of t with respect to x, because we have dt, ptx, and t, so this is the expectation of t with respect to the given position x, and then we have just a single integral of some complicated function px dx. Now we can see that this omega could be even further simplified. If we realize that the yx is after training the expectation of dx t with respect to x, then this term here, which we have, in fact also leads to 0. So this complicated formula until here is can be represented by a 0, and then we are really just left with the omega is 1/2 of this integral, where we have this directional derivative squared, and so we have here this tau, and we have here this gradient of y x, so it's a partial derivative of y with respect to x, which is our Jacobian matrix, and this is our vector tau. And if you remember from the tangent propagation we just discussed before, this is exactly the same form, except that we are dealing with a continuous form. So here we are showing that the tangent propagation and the actual transformation of the data by data augmentation lead to the same thing, in fact, and are tightly related. Now, this directional derivative, we can see that if this will be a regularizer, because we had this omega as a regularizer multiplied with this lambda, this will be 0 in case this directional derivative is 0. This means that the direction how the y-x changes when changing y with the x with some epsilon of tau, that it will be actually perpendicular to tau. So the y will be changing perpendicular to tau, and that will lead to this 0 here, and that will actually invoke this transformational invariance in the regularizer we were looking for. So every transformation which is slightly deviating from the untransformed in the way how the transformation is changing the particular input vector, that will be still the regularizer will have value 0, while for any other transformations the value will not be 0, and those transformations will be penalized, while these transformations we have designed the invariance for will not be penalized. As a final note, a special version where the transformation is just an addition of random noise is the so-called Tikhonov regularization, which overall it controls the complexity of the model. If you see here, the change, the gradient of y itself is penalized, so the function y should not change too much, and therefore the function y will be favored to be more smooth and not prone to drastic changes. Now let's discuss the third category of building in invariance into neural networks. And in this case, we will be talking about the so-called convolutional networks, which incorporate the regularization into the neural network architecture. So imagine we have a task of making a pattern recognition on digits, and if we would approach this problem from our previous material, we would likely build a fully connected neural network with 2 layers, which will be attempting to perform the classification of the digits into the respective classes. However, this approach would lead to a fact that as a fully connected layer, we would have a lot of weights, and we can already see on the examples of the digits we have seen before that many of the weights, the relationship between the pixels are somehow not really informative. And in particular, the pixels which are close to each other or far away from each other are somehow considered in the same way. While if we think about the problem of pattern recognition, there is the key insight is that the neighboring pixels are more correlated than the distant pixels. Therefore, it makes more sense to relate to each other neighboring pixels than some distant pixels. And that leads to a strategy of extracting local features from subregions of the image. So imagine that we have, just like here, we can see this frustum where we are having weights which are associated with the pixels which are in this sub-image, in this just a small rectangle within the image, and we are performing a linear combination of these pixels with particular weights, and this is the result of our of this linear combination, and it will lead to an feature based on this process. So we are not taking into account the linear combination of all pixels, but only of a small region, and this small region is having then the consequence that we are extracting local features from subregions. And information of such features can be merged in later stages to detect higher order features. So we can see that we have here another subregion, the red one. Again, there has been the weights have been used to perform linear combination of the pixels covered by this red rectangle here, and then we calculate the resulting feature from that. And as you can see here, these two features are then again combined in another level of this type of linear combination in order to create a new feature. And we can see, therefore, that while this one feature here effectively sees only this one part of the image, the other part sees another part of the image, which is then combined together. So this combination already sees much bigger subpart of the image. So then, and we can also base the strategy on the fact that features found in one part of the image can be useful also for other parts of image. So for example, if we have a number 6 here and one subregion sees a characteristic shape of the letter or number 6, then with respect to a certain shift, we would expect that there would be some other specific characteristics of this number 6, and therefore these local features can build together the global representation of a particular pattern, and can be in this gradual way from local features to global meaning being used for the task of classification. In the previous image, the feature was having a certain access through also the weights and the linear combination of the pixels to a certain area subregion of the image, and we call it, and this is also borrowed from visual perception science, we call this receptive fields. So the feature only sees a particular sub area, which is called receptive fields. Also, if we are performing a certain linear combination on a certain receptive field, then another feature from the same so-called feature map will perform exactly the linear combination of pixel values with the same set of weights, but on another area within the image. And we are talking about the so-called weight sharing. So we are not having weights which are covering the entire image like we would do in fully connected network. We are having a much smaller amount of weights per a certain so-called feature map, and this feature map is simply a result of applying this linear combination of the pixels within a subregion with a set of weights. And those familiar with signal processing can see this as another explanation of the process called convolution, especially in particular a discrete convolution. And therefore these networks are called convolutional neural networks. So what we effectively can this leads to is that we are performing, our weights are organized in one smaller kernel, we can call it also a filter kernel, and we are filtering our image with a particular filter kernel, and the results of this filtering are stored in a feature map. And we can also change this filter kernel to another one, and then we can filter again the entire image with this filter kernel, resulting in a new image, or actually new feature map. So we could have more feature maps, not only one feature map associated with one kernel, one set of weights, but more feature maps associated with more filter kernels. And then, so let's have a look at one example here. We can have a feature map which consists of 100 units, and in a 10 times 10 grid, so which makes it 100, and each of them is covering a 5 times 5 pixel patch of an input image. So this could be that our image could either be covered by these subregions in a contiguous and non-overlapping way, so meaning that these subregions are not overlapping, and then we will automatically, by the fact that we are performing this this linear combination of the 5 times 5 pixels, we can immediately see that this will also reduce the effective resolution of that image, because it will be the 5 times 5 region will be just represented by one feature in the feature map. Alternatively, another convolutional neural networks can be built in such a way that there is indeed an overlap, and it to such a degree that it is done exactly as a convolution, and in such cases the resolution of the image will not be made smaller, because there will be a almost complete overlap in these subregions up to, let's say, shift of one, but if we move from one pixel to a neighboring pixel in the feature map, or pixel or feature, we can say. So in a 5 times 5 pixel patch, we would have therefore 25 kernel weights, or weights, weight vector, which is associated with that feature map, and will have a plus one bias parameter. And then the outcome of this linear combination, or we can call it also linear filtering if we think about convolution, is then input to a nonlinear activation function. The reason why we use the nonlinear activation function is that if we would have also several of these convolutional neural network layers, then we want that that each layer is performing a certain operation, and these layers are not collapsible into a just a simple one layer. So if we have several stages or passes of convolutions, we can replace several passes of convolution just with one convolution. And this nonlinear activation function will introduce this nonlinearity, which will break the possibility of collapsing the convolutions from several stages or layers into a single one. So as we see this analogy to convolution, we can therefore see that recognize that all units in one feature map, all pixels if you like, all features detect the same pattern and at different locations in an image. That means that we are building here a certain invariance. As I already mentioned, as we are sharing these weights across different subregions, this evaluation is equivalent to convolution. Then, when I talked about the invariance, it means that if an input image is shifted for some reason, something has moved, a car has moved, the activations will be shifted as well. So imagine a car moving and we want to classify what is in the image, so whether the car is in the beginning of the image or in the end of the image. So there will be still some activations of that car identical. They will be just at a different position of the feature map. So therefore, we are building in convolutional neural networks an invariance with respect to translations. And as I said before, we have an example of just one feature map with its own weights, which are then shared across the subregions, plus bias. But typically, in convolutional neural networks, we would have multiple feature maps. So imagine that one feature map will be maybe performing some kind of a low-pass filtering. Another feature map will cause a edge detection, and another feature map will perform some kind of gradient in color space. All these type of weights are organized in these kernels will be, however, learned. It's not that as we are used from convolution and linear filtering, that we have some given filter kernels. In these cases, in the convolutional neural networks, all these kernels or weights will be learned exactly as we have been learning them for the fully connected networks before. So in case we are performing the convolution and there is like a strong overlap between the individual subregions, then the next step would be subsampling layer, which then further decreases the effective spatial resolution of the feature map, and it will also combine the receptive fields to a from a bigger region into one feature. Subsampling can be considered as averaging, for example, with additional weight and bias followed by a nonlinear activation function. As I said, receptive fields can be also designed in at being contiguous, so that they are just next to each other, but they are not overlapping. Convolutional layers can be organized in many layers instead of just one layer, like we have seen in the case of the fully connected network discussed before, where we had just two sets of weights, one in the hidden layer and another one in the output layer. So we can have many more layers, and typically we would have many more layers in the convolutional neural networks. And here we will further have the convolution and subsampling, and it will be increasing the invariance because these layers will be able to detect a certain pattern within an image, as this subsequent layering will be then activating a certain feature of a particular pattern in later stages at later layers. Typically, the convolutional neural networks has a kind of a pyramidal shape where the first layers of the feature maps would have the same resolution as the input image, or a similar resolution as the input image, and they would have a relatively few feature maps organized in one layer. However, the next layers will often have the reduced spatial resolution, maybe a half of that resolution, or effectively as in a 2D case, and quarter of a resolution, and in a case of 3D convolutional layers, in volumetric case, we will have even higher reduction in spatial resolution. However, each of these layers, while the resolution is halved, the number of feature maps will be increased, leading effectively that with each layer we will have less and less of spatial resolution, and towards the end of the network we will have only few of our elements in spatial resolution, and that in the final layer we will typically have a fully connected layer with softmax output nonlinearity in case of multi-class classification. So this type of network can be trained more or less exactly in the same way as we have been training the fully connected network using backpropagation. The same principle holds. However, there is a notable difference that we are using shared weights of these filter kernels, these convolutional filter kernels. And that means that we will, for each of these feature map units, we will be calculating the errors, and these errors will contribute to the vector gradient vector update for the updates of the weights, and this vector will be a summing up components from all these units. This means that all of the units will be affecting how this weight vector in one feature map is appears. So it is not coming just from one unit, let's say, but from many units. This leads, as a positive side effect, that as we do not have, while we have a lot of layers, we do not really have a lot of weights between these layers because we have these shared weights organized in this convolutional type of kernels. So we have a strong reduction of weights and parameters to train thanks to this sharing effect. Convolutional neural networks can therefore be seen as one way to incorporate invariance in neural network tasks, and it can be also combined with other types of invariances, like, for example, we would typically use the data augmentation in order to build in other invariances such as rotation, for example. The convolutional neural networks can be considered as a type of regularization from the perspective of the fact that they have this hard constraint on weight sharing. So each feature map is sharing the weights of this, we could call it a convolutional kernel. This has advantages that we have a much less demands on the memory requirements with respect to these weights. However, it also has some potential disadvantages of this hard constraint. We will be discussing now a case where we will have this concept of soft weight sharing, where we will encourage the weights to be similar to each other in a soft way. And potentially there could be another consequent step, which will then prune some of the weights, which are then become very similar indeed throughout the training. And this soft weight sharing will be realized through a regularization. So we will divide, therefore, the weights into groups, and they will be the groups will be represented by some mean, and spread of weights will be both determined by learning. So we will have several groups, and these groups will be represented by some kind of Gaussian kernels. The key idea is to encourage several groups of weights, probability distribution as a mixture of Gaussians. So we will therefore have this mixture of Gaussians, and the weights will be by the machinery of a regularization will be dragged closer and closer to the means of these Gaussian kernels. The weights will be learned, of course, during this learning process, but not only the weights will be learned, but we will be additionally learning the means of the Gaussian kernels, its variances, and also the mixing coefficients. So in the mixture of Gaussians, they will be also learned. Therefore, we will define a computational machinery to define how this soft weight sharing can be achieved. In short, this will be achieved by a regularization. So in addition to the regular error for the weights from the backpropagation, we will have a regularization term which will be securing that the weights are shared, and in this regularization terms, we will also have the process of learning of the means and variances and mixing coefficients. So let's start. Let's define some variables aj of the weights, which are defining as the mixture of quotients, where the coefficient j means now the jth quotient. So we will have a the weight is characterized by the normal probability distribution given a certain mean and variance, and as we are dealing with several quotients, with also a mixing coefficient. And therefore, a probability of a certain weight in this regularizer is associated with a sum of this mixture of quotients, where the j goes from 1 to m, to where the m is the total number of the quotient kernels, which is predefined. So we have here the formula for the mixing of one quotient kernel, and in sum will be all quotient kernels. This is for one weight component. However, if we have an entire weight vector now in the neural network, and this could be practically any neural network. Let's think of the two-layer neural network, which we have been discussing before conceptually. So, however, the probability of the weight vector is simply a product of the individual probabilities of the individual weights, where the iterator I here is now associated with the number of weights. And as these are individually drawn probabilities, we have here therefore the product. As typical for and used many times throughout this course in the past, we define an error function associated with this probability distribution as the negative log of this probability, where in the case of maximum likelihood, we would like to find out where this negative log equal to 0 to define the best parameters, and especially in the context of is equal to 0 if we are performing the derivative of this logarithm. So generally, we are interested in the finding the minimum of this negative log, of course. So, and this is this function omega here is therefore defining as the regularization term, which is the negative sum of negative logs of individual probabilities of these weight components. So, and therefore, we will now have a look, given the definition of these weight components, we know what this logarithm is, and we will from that devise different components of the regularization, or with respect to learning or regularizing weights, or learning parameters of the Gaussian mixture of quotients. So the total error function for the soft weight sharing encouragement will therefore need to be changed from the error function to an error function including the regularization by some certain amount of the regularizer determined by the parameter lambda. As we are dealing with several parameters, the weights, the means, the variances, and the mixing coefficients, we will all put them together into one big vector, if you like, and perform a joint optimization. This can be done with the gradient descent, but the book also is mentioning conjugate gradients or quasi-Newton methods as possibilities of more efficient process of learning. So our task now will be to determine the error components or the gradient components of the error, change of error with respect to the weights, change of error with respect to the means of this mixture of quotients, change of error with respect to the variance, and the mixing coefficients. So once again, we want to have, imagine that we have this mixture of quotients, and we want that within this mixture of quotients, the individual weights are dragged towards the centers of these quotient distributions. Let's start the strategy of defining all these vector components. So we can take the mixing coefficients pi j, and as before we did, we can regard them as priors, and so that we can express the posterior probability. The posterior probability now here is expressed as gamma j, and that is the aj of a particular weight. So here we do not have the index of the weight because it will be for all weights the same principle. So we have here, therefore, the posterior probability, where here we have the aj is representing the prior, the mixing coefficients, the likelihood function, which will be our normal distribution, and then we have the normalization term, which is all the mixing coefficients associated with their corresponding normal distributions. Obviously, as this is a posterior probability which is properly normalized, the sum of these gammas for each of the j, meaning each of the quotient kernels, will be therefore 1. So, and now we will use this gamma in the calculation of these individual components individually. So let's start at the concept of the soft weight sharing regularization, first by devising the gradient components for the regularizer, which are related to the weight regularization. So here what we want is that the weights are dragged to the centers of this quotient mixture of these individual quotients. This we will see how this comes to place, but first we will need to define certain quantities, like for example the sum of these AJs, which in itself is the quotient mixture entity, so the mixing coefficients and the quotient one of the quotient distributions in the aj. If we sum them up here, this will lead to a, which is this normalizing coefficient. So if we have this gamma being the posterior distribution, then the aj is the prior times the likelihood, so pi j times the corresponding normal distribution, and here we have the sum of all these normal distributions and the product with their mixing coefficients. So that's capital A. The therefore, for the definition of the gradient, we can see that it is we are looking for the negative log of this probability distribution, which is the negative log of the sum of the AJs as it was defined on the previous slide. And then we can see now, given the new definition of capital A, this is negative ln capital A. And we can add to that some two terms where one is positive, when one is negative, they are the same. So we have a term of sum of AJ divided by A. So this is in fact the gamma J times the ln AJ, which is forming one of these two terms. We will be, although these can be these are added and removed, so the result is 0, we will naturally mix it somehow with this ln A so that we reformulate our formulation to a new formulation, which we will be then using for devising the gradient components. So in the second step, we can see we have just rearranged. So we take this term, put it here. The plus term is afterwards minus ln A. And then we have here that this term is can be combined. These two terms can be combined together. So we have the ln A is now associated with the sum of AJ divided by A, sum of it, and that is sum of the gammas, and as the gamma is a properly normalized posterior distribution, this is actually equal to 1. However, it is also having the same structure as here, and therefore we can in the next step, we have again the first term here, and in the second term, we can, for these two terms, we can put them together in a way that the ln A we can put into the sum, and then we have the ln where this AJ divided by A and the ln AJ and minus ln A are combined together, where we can see we have here this ln AJ is here, this is coming from here, here is plus, the minus leads to the fact that the ln A goes to the denominator. So now we have only two terms. And then in the next step, we simply just replace these variables to their other meanings. So we have here, as we know, this is the posterior distribution gamma, and we take this minus from here to the minus ln AJ plus the sum of gamma ln gamma for a particular jth Gaussian. So that's the result of this reformulation, where we can see that this negative log of the probability is a sum of terms where this posterior probability distribution is showing up. At the same time, there is negative ln AJ, which is also now showing here, is simply, what is it? It's just an ln of the Gaussian mixture element, so its mixing coefficients and the corresponding Gaussian distribution parameterized by the mean and the variance, and that is simply if we are performing the ln of it, we will have the ln of the mixing coefficient, and then in this product it's just one component and it's minus because of this minus. Then we have the normalizing coefficients in the probability distribution, which is the 2 pi, and then we have also ln sigma of sigma squared of that's the variance, which are coming from this normalization term, they are both plus because we have the negative log. So minus has been turned to plus. And then we also have the exponent part of the exponent part of our normal distribution, where we have the wi minus mu j. So these are different indices squared divided by 2 sigma squared. So this is our negative log of the aj, and just we will call it, for the abbreviation in the next slide, we will call it the qj, to just simply avoid writing this whole term. So let's continue. We have this one result, and we have also now the formulation of the negative log of the aj. We are again restating that here on the top. Negative log of this probability of the weight is equal to the result, the sum of the gamma posterior with multiplied with minus ln aj, which is this long term, plus the sum of gamma jw ln gamma jw. So this is the result, and now we can perform the partial derivative with respect to weights to obtain the gradient. So the partial derivative here is partial derivative of this one sum term and partial derivative of this another sum term. These terms are the same as before, and now we can see how the partial derivative evolves. So this is a product. We can see there's a product of two terms. Of course, if we look at partial derivative with respect to weights, this term will go away. So we only will have this term contributing to the partial derivative. And its partial derivative of this term is first we perform the derivative of the squared function, so that will be a 2, which will be cancelled out with this 2, and then we have the partial derivative of the w, which is just 1. So we simply in fact just lose these 2 and this exponent by the means of the partial derivative. And it's a partial derivative of a product, as I said. So first, this gamma is not derived. It also contains the w's, because it has the normal distributions in its definition, both in the numerator and then the sum in the denominator. And also, so this is underived and this is derived, and then this we will leave as derived, and then we have the qj for representing this long part here, which is the underived part. And plus, and here we have the definition of partial derivative of the one term in the multiplication of these two terms, and then this is derived, this is underived, and then this is underived, and this is derived. So, and the derivation here is first derivative of the ln, which leads to 1 divided by gamma, and then times the derivative of the yj w with respect to the w. So we can see that both here we have this partial derivative, we have this partial derivative also here, and we have this partial derivative also here. So we can actually put them together into one sum. That will lead that we slightly reorganize these two sums, and one sum will just have this one product, which is the gamma distribution, posterior distribution, multiplied with this weight and difference with the, or offset of the weight from the mean divided by the variance squared, divided by the standard deviation squared. And then the other term here will be the partial derivative of the gamma with respect to the weights, and then this term here, which is the long negative log of the aj here, and then we have the ln gamma j, which comes from here, and then we have plus 1, because here we have simply just, after this cancels out, we have just this partial derivative, so then plus 1. And this sum, in fact, will be equal to 0, and that is for the following reason. First of all, we know that the sum of these posterior distributions is 1, because they are properly normalized. The first derivative of the distribution, therefore, in sum, is equal to 0. So we have these terms in sum will be equal to 0, exactly. So it's not just approximately, they will be equal to 0. And these are multiplied, these terms are here multiplied by some term which we will claim are in fact a constant. So we see here that the qj plus ln gamma jw plus 1, so this first term is the minus ln ajw, and this is here the ln of ajw divided by the sum plus 1. And now, if we are having these two terms, if we put these two terms into one logarithm, then we will see that the aj will cancel itself out, and we will just have this one sum here. So in fact, while we have this index j, this sum doesn't really depend on j, and it is constant because it's a sum over all the aj's or ak's. It's just this normalizing term will be really there, and then plus 1. So it's a constant. So a constant can be taken out of this sum, and this sum is equal to 0. So therefore, this part of the now it will be equal to 0, and therefore we have here as a result that the parts of the gradients which we are interested in the regularizer will be simply pulling the weight towards the center of the jth gaussian with a force proportional to the posterior probability. As it says here, we can see that this equation clearly does that. It's the regularizer is trying to minimize this distance, and also there is the gain is expressed by this multiplier here, which is the posterior probability. So therefore, we will formulate our overall entry into the gradients for the weights, which was originally just by the error term here from the network. We add this regularizer, which is a regularizer weighted by some lambda, and here we have this formula which we simply take from here, which expresses this regularization that the weight should be as close to the Gaussian center as possible for a particular Gaussian. So each of these Gaussians will be dragging, in fact, these individual these weights to their centers, and with respect to a certain force which is proportional to their posterior probabilities. Next, we will have a look at how do we learn the properties of the Gaussian mixture model, namely the means and the variances and the mixing coefficients. Let us have a look of what is happening through this regularization to the means of this Gaussian mixture model, and we can see that the result will push the means towards the average of the weight values weighted by the posterior probabilities. So similar effect as we have observed for the weights, but now the means will be also pushed to the average of the weight values. Now we start again with the same formula which we have for our error term, and then we will perform the partial derivative with respect to the mean of one of these Gaussian distributions, and that will in fact, so we can have a look here, it will in fact have a very similar effect as the W. It will be the result will be very similar, and in fact also this cancellation will be will happen in the same way, meaning that we will be left out only with this term to be performing the partial derivatives, and the rest will cancel itself out. And when we perform here this derivative, then we can see that the exponent and these two will again disappear, and thanks to this minus, we will have the minus value here. So this is just for one of these weights. We have this the constraint generated, this change will go that it will be the regularizer will try to put the mean closer to that weight. Now, if we do that for all the weights, we will see that we go towards the average of these weights, and this is proportional to the posterior probability gamma here. So this is our second term now for expressing the error with respect to the mean, which will be part of the regularizer and will be influencing the gradient of this joint optimization process. The next step will be we will look at the standard deviation. Now let's have a look at how we devise the gradients for the standard deviation. So we perform the partial derivative of this error with respect to the regularizer component of the error with respect to the sigma j, and that is therefore again just a we calculate this from the parts where there is actually the sigma, but the sigma is also appearing in here, of course, and here. But as we have seen in the previous cases, that will also cancel itself out. Therefore, we will be left with the term where we have the result of this partial derivative will be that we are performing derivative of this term and this term as a product with the posterior probability. The result is the posterior probability times the 1 divided by sigma minus weight minus the mean in the numerator squared, and then the sigma j cubed in the denominator. This can be also put into the under one fraction, under one ratio, and we see the final formula here, where we see that we are again having the sum of through all the weights, and we can see that the variance is the weighted average of squared deviation of the weights around the corresponding center. So the squared deviations of the weights from the center are here, and we are trying that the variance is close to this value here, and it is then also proportional or scaled by this posterior probability here. So now we have in our regularization the various terms. One is for the weights, one is for the means, one is special for the sigma standard deviation, and the remaining one will be for the mixing coefficients, which are mixing the Gaussian distributions into the mixture of Gaussians model. As the last aspect or parameter for which we need to devise a scheme for updating the gradient in the joint optimization are the mixing coefficients pi j. So these mixing coefficients pi j, we can perform the optimization or the search for the gradient with respect to the partial derivatives of the error function as before, of the regularizer part of the error function as before. However, we have a certain difference to the previous parameters, and that is that these parameter pi's, they are actually forming a they were regarded as prior, so they are actually forming a proper probability distribution. So the sum of the pi j's over all the Gaussian kernels which we have is 1. And also each of the pi j's is between 0 and 1. So it's like a probability distribution. And that causes a constraint. In our learning process, this constraint needs to be considered. And therefore, a strategy how to deal with this could be to realize that these conditions can be fulfilled if the pi j is a result of a certain softmax calculation of some unconstrained variable alpha. So you can imagine that each distribution of pi's over as priors we have can be realized by some softmax where we have some AJ's and or AK's in general, which are unconstrained, and they will result in this constrained pi j values which are between 0 and 1, and in some they are 1. So therefore, instead of searching for the partial derivative with respect to pi j, we will be searching for a partial derivative with respect to this alpha j, which is this unconstrained parameter. And by finding that, we will essentially find the what is the regularizer term for the pi j. Just for making some abbreviations shorter, we had previously the AJ, not alpha j as here, but AJ W. We summed up these weighted probability distribution, normal probability distributions of this Gaussian mixture model into this sum, which was this normalizing term a couple of slides back, that was equal to A. So we will use this A here as well in our formulation, just that our formulas are not exceedingly large. So let's start with our partial derivative of the negative log of the probability distribution with respect to alpha j. That is equal to, and now we will not be using the previous formula with this posterior distribution, but we will simply put in the sum of all alphas in the formula, which is the formula for the PW. So we have here the all the Gaussian mixture models in the negative log. And we want to perform the partial derivative with respect to alpha j. So first off, if we perform the derivative, so this is a chain rule, of course, and therefore we first will perform the derivative of the logarithm, and this in fact is equal to the capital A, and therefore we will have the result of this logarithm derivative will be 1 divided by A, and minus here because of this minus, so the minus is here, and then we will have the partial derivative with respect to aj of this formula here. Therefore, we simply have to look, okay, how are we performing this formula derivative with respect to alpha j, and we see that the pi j is directly here in this sum represented already, and then we have these probability distributions, normal distributions. However, there the pi is not really represented, and therefore this can be regarded as just some multipliers. Therefore, let's see what is the derivative of pi k with respect to aj. So it is a derivative of a softmax, in fact, because this is we are performing the derivative of the softmax, and that we know from the previous chapters that it has a resulting formula, which is in case the k is equal to j. If we have partial derivative of pi k with respect to alpha j, if the k is equal to j, then we have the result similar to the sigmoid, which is pi j times 1 minus pi j. And if they are not equal, we have minus pi k times pi j. So this can be also formulated by one formula, which has the Kronecker delta, as we will see in the next. So this formula derivative is equal to, we move the derivative to here because this is not, we do not perform derivative of this part. There is no pi or alpha for that matter. And that is equal to, therefore, to the derivative of the softmax, which is here written as pi k times Kronecker delta, which is either 1 or 0, and it's 1 only if the j is equal to k, minus pi j. So if j is equal to k, then it is pi k 1 minus pi k, or pi j 1 minus pi j, and if it's not, then this is pi k, this is 0, this is pi j, so we will have as the result only minus pi j pi k. So we can formulate that here. So in this formula, we simply, therefore, we can take one case out where the j is equal to k, and for that case, that part of the formula is expressed here, where we can see that it is this normal distribution with the parameters j are multiplied with the pi j 1 minus pi j, and then for the rest, where the k is not equal to j, we have the rest is which is the minus pi k pi j and the probability distribution multiplied with those terms. And now we can see that we have pi j here, we have pi j also here, so we can take it out, and we will end up with now 1 times this normal distribution, which we have here, and then this normal distribution times minus pi j. And then we have already taken out 1 pi j from here, so this is just 1 pi k minus pi k and the normal distribution, and now we have 1 normal distribution times minus pi j, so we can cross out this part and add that pi j and that normal distribution back into the sum, and therefore we will have our formula where we have the pi j out, and then we have the normal distribution of with the weights mean mu j and sigma squared j, and we have the sum of all the mixture of quotients together. And that leads to realization that we have here, if we multiply this with this and put it on the together with this denominator, it is equal to what? It is simply equal to the posterior distribution yk of w. So these terms, and then if we take this term and multiply it with the pi j and this term, so the a and this term are in fact the same, and they are minus minus, so that's plus, so it will be the same term, a divided by a times pi j, so we will end up with the resulting formula, which is pi j minus gamma j w is the resulting formula. Now, if we sum it over all the w's, we have this formula, which actually tells us that the gradient of the error with respect to the a alpha j is drives pi j's towards the average posterior probability for component j. So here we see how it drives to the average posterior probability for component j through this sum. And that is the last part of our gradient of our regularizer term. And with that, we have all the error or error changes with respect to the various quantities expressed, and we can perform these partial derivative updates and use it in our update of our weights, of our means, of our standard deviations, and the mixing coefficients, so that we jointly optimize them, and we will by that define our Gaussian mixture model, and we will define the weights which will be then driven to have similar values within this mixture model distribution. Next, we will be talking about the so-called mixture density networks. The task of machine learning in many cases is to model a conditional probability distribution. So given an input x, what is the probability of a target t? And in this regard, we have two related directions of problems. The first of all, there are so-called forward problems that are characterized by solving a certain problem by applying known parameters in a formula that leads to a desired solution. So, for example, we will have here a certain function of angles. So our input is the angle of this robotic arm with this single elbow joint, and the result of it is the position x1 and x2 of the end effector here. So this is a forward problem. We apply parameters, and their application leads to the result. It's straightforward and has one solution. Then there we have a set of problems which are called inverse problems, and these are defined by knowing the desired state, the end state, let's say, but the corresponding parameters to it are unknown, and they are to be found out. And they often can have also more solution, and they can be multimodal, and that is the issue we will be targeting with these mixture density networks. So we can see that here on this example, where the robotic arm is given just by an inverse problem solution, given the position of the end effector x1 and x2. And that leads to we should find out inversely what are the corresponding angles as parameters that define this end effector's position. And we will find out that there is not just a single solution, but there are two solutions, because this is the solution elbow up, and this would be another solution elbow down. So we can often have two solutions to this problem, and that leads to certain problems, as we will see just in a second. Here is another example where we have a simple regression problem where we have the set of input points, and they are governed by the certain signal and then perturbed by a certain level of noise. And we can see how the mean of this regression is nicely matching our sample point distribution. So here we have a function of x scalar between 0 and 1, and it is giving us an y predicted value between 0 and 1. And so here, in this case, the actual mean is really matching our sample points well. Now, however, imagine that we perform inverse of this function, and so we basically reflect the sample points around this axis, and our samples will be distributed in this way. So in this case, we will have not only one sort of, some cases we will be having several modes, if you like, of the distribution, and this is not a unimodal distribution per given t, as we can see in this case. Here we have multiple modes, and that is leading to the problem that our mean, the conditional mean, will perform rather poorly, and we will not have a very good match between our input sample points and the predicted value y. And that is often the case in inverse problems, because the inverse problems have multiple solutions. Like we could see, for example, here we could have multiple solutions, or here, and that is not very well represented by the conditional mean. So the conditional mean is problematic in these cases, and we need to develop a solution that can handle this problem well. And in that context, we will be talking about the mixture density networks as a general approach. So a general framework for modeling conditional probability distributions could be to model it with having several, mixing several densities together to form a desired probability distribution. Like, for example, the mixture of quotients, which we have been talking about just a few slides back in the context of soft weights. We can approximate with the mixture of quotients a multimodal probability distribution, as we can see here. So, and with that, we will have the modeling the conditional probability distribution will lead to a more powerful representation from which we can then obtain various quantities. Now, the general concept here is that we will, based on our, let's say, regression problem, which we have seen just on the previous slide, we can train, let's say, a two-layer neural network. So we have an input layer of x1 or 2 xt, then we have the hidden layer with some nonlinearities like 10h, for example, and then we have the output layer. And in this output layer, and of course we have a fully connected network with the corresponding weights, and in the output layer we will now have the output. However, instead of having just a single prediction of t as the output, we will have the parameters of our conditional probability distribution as the output, meaning that we will have here various parameters of this probability distribution. As we said that we are dealing with a mixture of Gaussian, the parameters for mixture of Gaussian is naturally the mixing coefficients pi for all k Gaussian lobes which we are mixing in this probability distribution. Then we have the means and the covariance matrices, or in one particular case which we are presenting here, just a variance parameter which will be the scaling parameter of the identity matrix. So we will have an isotropic Gaussian probability distributions. So we can have a two-layer 10H two-layer network with 10H activation in the hidden layer with k Gaussian components and with L-dimensional target outcome. So if the T is one-dimensional, so we have a scalar, then we have just L is 1. If it's two-dimensional, then L is 2. And we have therefore, in this output layer, we would have k activations for pi for mixing coefficients. So actually the ak pi will be activations related to the mixing coefficients, and we will see in a minute how. And then we will have also k activations for the ak sigma for the kernel width. So that's the parameter related to our sigma, standard deviation or variance. And then we have the L times K activations, AK mu for means. That means that for each normal distribution, we need a mean, and this mean is L-dimensional, and we need k of them because for each of the Gaussian lobes which we are mixing. So these are the activations in the output layer, which are actually the parameters of this Gaussian probability distribution, or the mixture of Gaussians probability distribution, to be more precise. So now, how do we calculate these parameters? The output of the network essentially is giving you the parameters, the pi, mean, and sigma, which are the parameters which are associated with one particular x input. So it's a conditional probability distribution which is multimodal. And now we can see that again we are dealing with the situation where the pi is constrained, of course, again because it is also treated as a prior distribution, these mixing coefficients, and therefore it is between 0 and 1, and their sum is 1, and therefore we can again model it through the softmax, where we have the AK activation as a term for the exponent of E, and then we have the sum of these exponential functions as the normalization term in the softmax, giving us the probability distribution entries for pi. So we have outcome of this network which we train being this the AK pi's, and out of that we will obtain the pi's actually for each of the Gaussian lobe in the mixture of Gaussians. The second aspect is, which we didn't mention before in the soft weight sharing, is that we would like that the sigma parameter is actually bigger than 0. So this is also a constraint, and we can model it simply by having the it as an exponential e powered by the ak sigma. So we have this one parameter is an argument of the exp function, and we will therefore model the sigma this way. And for means, we simply have the mean equal to the activation itself, which is associated with the mu. So we have all these output values at the outcome, and from those we will be generating then the pi's, sigmas, and mu's, which were defining our conditional multimodal probability distribution. As always, we devise the error function, and it is done in a usual way, where we have here the negative logarithm of the sum of this mixture of quotients, and we already have seen, so this is in general multivariate case, both for the input vectors, the output vectors, and then of course the corresponding means then as well. And as we have done for the software sharing, we represent the this fraction of one of these Gaussians, and with respect to the sum of the Gaussians as a posterior probability distribution gamma, which is y and k is the yk for a particular training data point. And we can therefore use this quantity in exactly the same way for defining the gradient of the error with respect to the activations. So with respect to the activations, also thanks to the constraints, we also devised previously that it is equal to pi k minus gamma nk. So that is the result which we will be using. Then the second one is the partial derivative of error with respect to ak for the means, and that is exactly the same as we had in the case of software sharing. So we take that as well in the same way. So these are the errors which we are using in the backpropagation associated with the output units. And then for the sigma, we will see how we devise this formula, which is here, which is slightly different from the one which we have seen before. And the reason is that we are here now incorporating also this constraint, which we ignored before, that the sigma k has to be equal or bigger than 0. So, and therefore we represent the sigma k as the e powered by ak sigma. So let's have a look at how this equation came to place. So we will be proceeding in the usual way. So we have the normal distribution parameters defining as the actual formula, which is here in this case a multidimensional multivariate Gaussian, and we can see that we have here the exponent L divided by 2, because L is the dimensions of the of our target outcome, and our sigma is actually the Gaussian here is is having the isotropic covariance matrix, and therefore we have a relatively simplified formula here. And if we perform the negative log of this distribution, we will end up in the various terms as we are used to, where we only pick those which are somehow related to the sigma k, and one of them is L divided by 2 coming from the exponent ln sigma k plus, and here we have this exponential term as well. As we have minus here, these terms which would be otherwise negative are positive, and we ignore the other terms because obviously they are not containing any sigma variable, and through the derivative will be equal to 0. So now we perform the partial derivative of this term with respect to sigma, and here in this case we are bringing in already this posterior distribution gamma and k, as we have seen before. So this term here is the one where we had gamma and then ln minus a was the term which we have. This is the term here now, and then we have some other terms which were characterizing our error, but those are not dependent on those will be cancelled out, and we will, as they have been cancelled out before in our software sharing, more thorough devising of those formulas. So here we simply just perform the derivative, and the derivative is equal to this formula. So both the terms in the bracket and also for gamma both are containing the sigma. So we have here taken a shortcut, but this is the result of the derivation, and the reasons why are analogous to those we have been discussing in the software sharing. And from this we can therefore devise further steps how our the gradient components will be determined. So the gradient partial derivative of error with respect to the activation is equal to the partial derivative of the sigma with respect to the activation, and then the partial derivative, this partial derivative, which the result is here. And this partial derivative is simply equal to, so the sigma k is equal to the a powered by a k sigma. Therefore, the derivative of this partial derivative is simply the e powered by ak sigma times the, and here we have taken out 1 divided by sigma from here, so that we have the L isolated, and here we have the square term. So, and actually this is equal to, again, the sigma k, and therefore these two terms cancel itself out, and our result will finally be that the gradient for the activations associated with the sigmas are equal to the gamma and k times the L minus, and then we have the squared difference between the training targets and the means divided by the variance sigma k squared. So with this, we have all the error functions determined, and the backpropagation will then serve for the purposes of obtaining the weights, errors, updates, and we can perform the optimization in order to, using gradient descent, find out the corresponding weight values, which will be giving us then the appropriate parameters for this mixture of Gaussian model, which we have been using the network for to estimate the parameters. With being equipped with the logic of how these mixture density networks are coming to place, we are coming back to our original example where we have inverted this regression function, and which was having a very poor conditional mean, and we are having a look at this what is happening to the training such a network for on this type of input data. So here we can see on the very right image still this input data with these green dots, and we have this network which is consisting of 2 layers, a hidden layer with 5 hidden units with the 10H activation function. It's a fully connected network, and we have decided to use 3 Gaussian components to somehow map this representation given by the samples. Here we can see that the conditional values per individual parameters of our Gaussian mixture model, and we can see that this is the diagram where we change the x on the horizontal axis, and on the y-axis we have the mixing coefficients pi, which are changing based on the x. So for the x here we see that the third coefficient is almost 1, while the other 2 are almost 0, and then we are gradually decreasing the 1 Gaussian element as we are progressing in the x direction. Then the second component, which is Gaussian, which is aligning here, is gradually taking over in this mixture of Gaussian, and then after, so from this point approximately, the last Gaussian lobe is becoming the most dominant one in this multimodal probability distribution to model this distribution of the samples. So we can see how these, if you can consider them as a soft switches, are acting upon turning on dominance of one or the other Gaussian lobes in representing this multimodal probability distribution. In the second diagram, we can see how the means are changing over the according to the x. So it's a conditional probability distribution with respect to given x for now the activations associated with the means, and we can see that the prediction for the means for the first Gaussian lobes are like this, so it aligns approximately with this Gaussian lobe, and then the other one, the second one, which is basically getting dominant in the middle, is having kind of an opposite direction, the means, and the third Gaussian lobe here is looks approximately like this, and that is mostly switched on, if you like, towards the end, towards the axes which are closer to 1. So we have in total for this neural network we would have 9 outputs, and so 3 outputs, 3 scalars will be associated with the mixing coefficients, 3 scalars will be associated with the means, and 3 scalars will be associated with the variance in this case. Now, we can do various statistical operations from this multimodal probability distribution, and one which would make sense is to observe the conditional mode. Conditional mean will again not make so much sense, because if we are performing conditional mean, the conditional mean will end up in locations which are not really viable, because it will need to be a functional curve, which obviously for the same x we are having largely different values in these multimodal regions, and that will be not very well captured by this conditional mean. Conditional mode, on the other hand, will create a kind of a discontinuous intervals on which we have a different mode, meaning which of these Gaussian lobes is somehow the one which maps, or which the best represents the function. And for that could be in one way, either can be found out with iterative methods, but also an alternative could be to consider it from a perspective to take always that Gaussian lobe, that Gaussian probability distribution, which has the highest mixing coefficient, and take the conditional mean only from based on that part of the probability distribution, and that will give us a reasonable approximation of this function again. So this was an approach how we, instead of having as an outcome of the network to have simply the value y, which would be the regression function, the conditional probability of t given y given x, but instead we are having a multiple outputs, in this case 9, which are in fact modeling as Gaussian probability distributions in the sense of a mixture of Gaussian settings, and the weights are therefore updated based on the error terms which are associated with these various quantities, which are the mixing coefficients, the means, and the variances or the scalar multipliers of a covariance matrix. So far, we have been dealing with neural networks in a way that we determined its parameters, its weight, by using the maximum likelihood estimation framework, meaning that the error function was simply maximizing a log likelihood or minimizing a negative log likelihood function. And based on this error at the output, we will be then evaluating the errors associated with different units in order to evaluate how we can update the weights in the gradient descent iteration. Then we also have considered regularized neural networks, where we could have this error simply error enhanced by the regularizing term. And we have been talking about various terms that could be used for such purposes, and it's related to maximum posterior estimation, where the regularizer with the regularizer as a logarithm of the prior parameter distribution. Now, at this point, we will be looking at the Bayesian neural networks, where we need to perform the Bayesian treatment so that we are marginalizing over the distribution of parameters for prediction. So to make a predictive distribution, we not only need to make a pointwise estimation like the weights, which maximum likelihood, or with maximum a posteriori estimation, but we need to actually weight all the conditional probabilities with the probabilities of the associated weights and perform an integral over the entire space of the possible weight values. And that will give us the predictive distribution, which we are looking at into when we are performing the Bayesian treatment. So we will be looking into this, and we will see how this problem is becoming more complex in the case of neural networks as compared to regression in linear models or classifications models. Also because we will have this highly nonlinear behavior of the neural networks, which do not allow us to deal with simple functions like quotients, like it was the case in linear models for regression. So let's start with the discussion on Bayesian neural networks for the regression case. So imagine we have again a two-layer neural network where we have a hidden layer, we have the output layer, and at the output layer we simply have the output is just simple a scalar value, which is the output function y. And we can characterize this neural network as through this probability distribution, where the likelihood of a given t obtaining a certain value is characterized by the normal distribution with the mean at the value of the y function, and the noise variance or noise precision beta is another parameter. For this time being, it is a given parameter, and we will see later on how we can pointwise estimate this type of hyperparameter from the data. Then the second probability distribution is not associated with the target values, but with the actual weights, and that's our prior, where we are describing that our weights are also normally distributed around 0, and we have a certain hyperparameter alpha, which is governing its covariance. As we can see, this is a multivariate Gaussian with an isotropic covariance matrix or isotropic covariance. So if we want to perform the calculation of the likelihood function given the training data, we will obtain it by the product of these individual normal distributions from all the data points, and having this and having the prior, we can therefore express our posterior distribution. So posterior probability for weights given the data and given our hyperparameters alpha and beta. So given the likelihood function and given the prior. So this is all stuff which we already know. However, from the regression, however, in this case, as imagined, we have these hidden units, and in these hidden units we have a nonlinear activation that leads to like 10H, for example. This would lead to the fact that our y function is behaving nonlinearly, and therefore this posterior distribution will not be a Gaussian. And in order to deal with this problem, we will approximate our posterior with a Gaussian function using the Laplace approximation. We have been talking about the Laplace approximation before, and basically this task boils down to find the mean and the covariance matrix. the mean, we will estimate from the maximum a posteriori estimation, so of the weights. So this will be the WMAP, and the covariance matrix will be coming from the Hessian matrix and our hyperparameters alpha and beta. Let's have a look at this. So in order to find out the posterior distribution, we will be performing the Laplace approximation using the regularized sum of square error function to find the WMAP. Here we can see we could have the error function, which would be the negative log likelihood, and we will be minimizing this error function, or we can have just a log likelihood and trying to maximize this function, and by that we will find the appropriate weights W. So for this time, we again assume that the alpha and beta hyperparameters are already given. The gradient descent or conjugate gradients can therefore be used together with the backpropagation in order to find these most likely weights, simply that we are performing this iterative approach through optimization to find the weights vector through the maximum a posteriori estimation approach. Then, once we obtain that, then we have our mean for our Laplace approximation of the posterior distribution, and then we need to still compute the covariance matrix. The covariance matrix is inverse to the precision matrix, and the precision matrix A is determined using the second derivatives of the negative logarithm. So where here is the function, this is the negative logarithm here, and the second order derivatives twice the nabla operator of our posterior. And we have already seen it before in the regression that we will be dealing essentially with finding this type of matrix where the alpha is multiplied with identity matrix and beta is multiplied with the Hessian matrix. This Hessian matrix is simply if once we calculate the gradient of the error function, gradient of the error, then once we perform once again the second order derivative of this Hessian matrix, we obtain it. We had several approaches how we can approximate or actually exactly calculate the Hessian matrix already discussed in this context, in the context of neural networks, by means of the backpropagation. Once we have this, we can approximate our posterior probability distribution for this regression case by this distribution Q, which characterizes the probability of the weights and taking into account the data and the hyperparameters alpha and beta. And it is a normal distribution of the weights with the mean at the WMAP, and its covariance matrix will be the A inverse. So now our task is to determine the predictive distribution of a T given a new input vector X, which is not part of our training set, and then we have as given our training set T and the hyperparameters A and B, and that is defined as an integral over this conditional probability of T given X, one for a given set of weights, and for a parameter beta, and this is multiplied with our posterior probability for the weights given the data set and these hyperparameters. So unlike in the other cases where we were simply performing the probability distribution and assigned the probability for a given for a T given a certain X based on some point estimate, either through maximum likelihood or maximum a posteriori for the weights. Here we simply have the entire probability distribution of the weights, and we take into account all the conditional probabilities for all the possible weights, and that is weighted by the corresponding probability of those weights. And this is what this integral is basically therefore representing. So our predictive distribution will take into account all the possible weights and their associated probabilities in order to create a predictive distribution what the values of t could be given the input and the training set and the hyperparameters. Now, in the case of the linear regression, we were able to define this analytically. However, in our case here, we have a problem that the y is non-linearly dependent on the w's, because we also have these activation functions in the hidden layer, which are performing a nonlinear operator on the linear combination of weights with the input. And therefore, the integral as a result will not be analytically tractable. That means that we cannot simply integrate this easily, and we need to approximate it. One strategy could be is to assume that our posterior probability distribution for our weights is having a small variance. This means that this Q, which is a normal distribution for our weights, has a mean and high probability associated with the weights at the mean and around at the very small neighborhood of the mean, but a little bit further away from the mean, the probabilities will be already very low, close to zero. So we will have a very small variance for our weights, and it will not be a point estimate, but it will be like a very sharply defined probability distribution. That is our assumption. And under this assumption, we can also represent the x, y of x and w as a through Taylor expansion series as a linear function. So instead of this nonlinear function, we will have a linear function where we will have the yx will be at the weights MAP. So we have now the x is this x, this is a new input vector, and then we have we can choose what weights we want to have in our network, and we will choose the maximum a posteriori weights, the highest, which are associated with the highest probability. And that will be our y value for our Taylor expansion series at the known point. And then we will expand it with the linear term here, where we have some kind of a g, which is then associated with the w minus WMAP. So this is our point at which we know, and this is the small neighborhood from that point, and this is multiplied with the first order derivative of the function y with respect to the w, and this gradient will be having the values at the WMAP. So the weights are at the point WMAP. So those coordinates for the weights. So that will be our term here, and we will therefore, once this is a linear function, we will generate a conditional probability which is so this term, which is in itself having this nonlinear yxw. Now we have it linear, and we will have a normal distribution of a t given a mean, which is a function of x, and it's also a function of the w here, and what the x is for this particular one case when we want to predict it, the probability distribution at this input vector x is fixed. So the w is our variable, and we have this kind of a linear function of W here for the mean, and we have this beta representing our precision and beta inverse the variance of this single variate normal distribution. This is the approximation of our conditional probability here, and we will see once we approximate it with this representation that we will be able to solve this integral analytically or through these approximations. Once we have made these approximations, we will use some general results which we have obtained in the past in this throughout this course for the purpose of the linear Gaussian model. So in that case, we knew that if we have a probability distribution P of x, which is a normal distribution, multivariate normal distribution, and we have a conditional probability y of x, which is also a normal distribution for y, where the mean is actually a linear function of the random variable x, and then it has also some covariance matrix L inverse. And if we have these two probability distributions, the marginal and the conditional one, the marginal with respect to y, which is governed by this linear transformation of the mean given the random variable x. Here we can see that this is the result for the normal distribution, where we have here the mean is the A mu plus b, and then the covariance matrix is coming out from these terms. And I'm not going to devise it now because we already devised it in the section 2. We spent quite some time on that, and therefore now we will just use this general result which we have obtained. In our case, so by analogy, we take this case and we apply it on our case where we have our normal distribution Q of W given the data set and the hyperparameters. So that is a normal distribution with a mean at WMAP, and its covariance matrix is the A inverse. And please note that now we have some kind of a naming overloading, because we have in our template case, we have A, which is here, and we have this A here, but these are two different A's. So unfortunately, this will lead to a little bit of confusion, but let's try to get out of this confusion by explanation. And then, so this Q probability distribution is related to this marginal probability of x. So we will see that this random variable x is actually, in our case, the random variable of weights W. And then we have the conditional probability T of the given x and the W. So, and we see that we have here the linear transformation of our W here. So we can see that this is like we have here this AX plus B. So we have something similar here, where the AX will be, in our case, the G transpose W will be the AX, and the plus B will be the rest of this. So this is not the AX, this is B, and the G transpose WMAP will be also part of the B. And then we have the beta inverse for our variance. So now we have these two. One is the marginal, one is the conditional one, which is having this linear function of the marginals random distribution variable, random variable W, and therefore we can define that the marginal of T is equal also to the normal distribution with the with a mean and a variance. And now let's define the mean and variance. So this mean is actually computed here. So A mean plus W. So A is our G transpose, and then a mean is the what do we put in for the mean? The mean will be here, so that is the WMAP here. So we put into this function for the mean, we put WMAP. So that will lead that this term will be 0, and for our mean we will therefore have this function yx at the WMAP, and we will have some kind of variance, and this variance is calculated in the following way. So we can see it here, L inverse plus A lambda inverse A transpose. So that is the L inverse is in our case beta inverse. So this is here, and then plus, and then A is in our case G transpose, and then lambda inverse is here our A inverse, so A inverse here, and then again the A transpose, which is in our case then G transpose. So this is the result for our variance, this is our result for our mean, and so our probability distribution, predictive probability distribution, is simply a normal distribution after these approximations, which has a mean of y of the input vector x by fixing the weights at WMAP, and it has the variance which is governed by the, and here it's written, and variance is associated with the noise in the target variable, so that's this beta hyperparameter, and x-dependent uncertainty in model parameters W, which is expressed here through this function here. So with this we have already defined our predictive distribution for the case of regression. Now we have also said that this variance is associated with the noise in the target variable beta, but we have for the case of this discussion, we have only set it or assumed it is fixed, or it is already somehow given. And now we will be again discussing how can we obtain the alpha and beta, as we did it already before by utilizing this evidence framework. So we will be dealing with this marginal likelihood, and which will help us to define what are the point-wise estimates for alpha and beta just by observing the data itself. So let's have a look at how this can be done. So hyperparameter optimization of alpha and beta, what is the maximum likelihood associated with these hyperparameters? We will simply do it by point estimates of the based on the evidence framework by maximizing the probability of this marginal likelihood. So the marginal likelihood here is defined as the, if you remember, if we have a posterior distribution, we have in the numerator the prior and the likelihood, and in the denominator we have the scaling factor, which is the sum of all the training points and all the weights. So we have that term here, and we have here the prior, and we have here the probability of the given W and B, which is basically our likelihood function. And now we can simply just perform the logarithm of this function in order to obtain our in order to be able to find out the maximum of this associated with the alpha and beta. So what is the maximal value of this probability given the alpha and beta, for which alpha and beta we will obtain the highest probability value. So, and this is approximately equal to, and as we have here in the case of regression, we have here this normal distribution. This is also a distribution where we have this sum of square differences in the exponent of the normal distribution. So here we have this error associated with the WMAP. So that's where the terms where the WMAP comes in. And then we have the other terms which are characterizing the log of marginal likelihood, and also characterizing the complexity of the model, as you remember, perhaps. So there are these terms which are associated with it, which come naturally out when you are performing the logarithm of this function here, and we have here therefore the sum instead of the product, and here is our square term at the point estimate of WMAP. So we have the MAP is here for the weights, and now we can express, which we already did before, so we are again not going to devise it, that our alpha is equal to the sum gamma divided by the WMAP squared. So, and the gamma itself is a sum over all weights, and where in the numerator we have beta times lambda I, and in the denominator we have alpha again plus beta times lambda I. Sometimes I think in the book the beta is somehow integrated into this lambda, and it's not mentioned explicitly. In our case here, these lambdas are coming from our Hessian matrix, and which is obtained as the error, second order derivative of the error with respect to the weights. And we had the discussion how we calculate the Hessian matrix before. And then once we have the Hessian matrix through the eigenanalysis, we obtain our lambdas. Now we can see that the gamma itself is containing a certain alpha here. So therefore, we have to iteratively, by setting the alpha and beta to some initial values, we can calculate what is the gamma. Based on the gamma, we calculate what is the new alpha, and then we need to recalculate, given that new alpha, what is therefore then the WMAP, because that is changing based on our hyperparameters, of course, and the beta is calculated similarly. So we have here our gamma again, which is a function of the beta itself, and therefore we have to do several iterations of where the beta precision of our noise is put into the equation to obtain the new gamma, and then from the new gamma we obtain the new beta. And after several iterations, once these parameters will converge to certain value, we see that these are the point estimates for which our marginal likelihood or our evidence is becoming the largest. So this is the way how we, again here also for these Bayesian neural networks, will be calculating these hyperparameters if we want to have them based on the data points themselves. As the last part of our discussion about the neural networks, from the chapter on neural networks, we will be discussing the Bayesian neural networks for classification, and we will just take only the simple case of two-class classification, where some point either belongs to one class or it doesn't belong to that class, which means that it automatically belongs to another class. Now, we will be proceeding very similarly or analogously to process steps that we discussed for regression. However, in the case of classification, we have one additional nonlinearity. For regression, we didn't have a nonlinearity in the output layer. We had only nonlinearity associated with the hidden layer units, and therefore, in this case, we will need to deal with this nonlinearity in the output layer unit for the case of classification. So we can define our likelihood function as belonging to a, so previously the likelihood function of would be associated with a certain, the y will be either powered by Tn or 1 minus Tn will be powering the 1 minus y, and then this was the probability for the entire training set would be the product. Now we perform the logarithm of this in order to perform the maximum likelihood estimation, or as we would do normally, and so maximizing this ln term of the likelihood. By ln, we, instead of the product, we have the sum here, and our exponents are becoming multipliers, and our terms associated with y or 1 minus y are becoming the arguments of a logarithm. So we are pretty much used to this and cross entropy formulation, and now we can use it for defining our error term. So we want to minimize the error, therefore we minimize the negative log likelihood, and by that we also, in this case, perform the regularization. So we want that our alphas, so that our weights are following the normal distribution, where the covariance matrix is essentially a diagonal matrix with the entries alpha in the diagonal. So after we perform the logarithm of this prior, then we will get the error term as here. So we have skipped a lot of steps here because we are already familiar with that from our linear models for classification, where we did all these steps, and also we just had the regression case, which was more or less analogous until here, except that we are not having sum of square differences here, but the cross entropy as our error function. Then this way we can perform a training of the neural network, and as we have this regularization here, we will therefore, this will be associated with training the WMAP. So this is not the maximum likelihood estimation, but maximum a posteriori, as we have our prior here, which will be serving as a regularization term in this error term here. And this could be determined, therefore, with the backpropagation and then with some iterative optimization scheme like conjugate gradient or gradient descent or the like. Then once we compute this WMAP or estimated, then we can actually use it for defining our posterior probability distribution, which is for our weights. However, for that we again need to calculate our Hessian matrix, and our Hessian matrix will be calculated from the second order derivatives of our error, and that we know how to calculate it either with approximations which were discussed before, or by some exact methods which we discussed before as a part of this chapter. So up to this Gaussian approximation or Laplace approximation, to be truthful to the name of the technique, the posterior or probability distribution for weights is analogous to regression. So, and now let's have a look at the next steps. We also have a hyperparameter alpha, which is characterizing the spread of the weights. And this hyperparameter alpha we can also estimate from our data by meaning of maximizing the marginal likelihood. So we make the point estimates of alpha. Note that in this case of classification, we do not have beta because we assume that in the training set there is no noise in the classification. So all of the points of the training set are properly classified. Now, therefore, we are just taking the marginal likelihood, and we are performing logarithm of it, where we will have a term of the error term associated with the WMAP, and then we will have some of these terms here which are characterizing the complexity of the model, which are associated with our prior. So these terms come from our prior normal distribution, as well as this term. In fact, this comes from the exponent, and this is part of our WMAP, which means that the error term where the WMAP is an argument. So this is in the cross entropy, and in the exponent from the prior where the WMAP comes to place. So once we are calculating this logarithm of this marginal likelihood, or the evidence of the which characterizes the complexity of the model as well, then we can maximize it given a certain alpha. So for a particular alpha, we are trying to find where the probability will be maximal, and we can do it in some iterative scheme again, where the alpha will be therefore estimated in an iterative way, where we have again the formula for the alpha as we have seen it before, depending on this gamma, and divided by the square of the WMAP vector, weight vector, and then the gamma is very similar to the previous definition of the gamma, except that we do not have these betas here, because these betas are actually non-existent in the case of this classification with a correctly classified training set. So and we can see that alpha is here and gamma is here, so we need to iteratively find out what is the alpha, so that until it converges. So with this approach, once we calculate the alpha, we will again need to calculate the maximum a posteriori estimate of the weights, and again out of that we calculate alpha, and through several iterations we can reach to the value of the hyperparameter, which corresponds to our actual distribution of the weights as a normal distribution of the weights with the mean of the WMAP and the Hessian matrix characterizing the covariance matrix, or actually the precision matrix, and then the covariance matrix out of that as an inverse. So once we have calculated the alpha, we can proceed in obtaining our predictive distribution. Now, Again, we want to use the same strategy, and we can say that our posterior, which is the posterior probability of the weights, is very narrow, and we can say that it's so narrow that we can make a point estimate of our predictive distribution. Instead of the predictive distribution, we will have here this conditional probability of t given the new input vector x with the fixed weights WMAP. So this is one approximation of the predictive distribution. So, however, we can make a more accurate Bayesian treatment by means that we will be dealing with the actual probability distribution of the weights and not only point estimating the weights by the posteriori estimation. In this case, however, in previous regression case, we have been performing a linear approximation of our function y, and in this case, we have the sigmoid, which makes the situation complicated, and due to nonlinearity of the sigmoid, we can make only the linear approximation of the activations and not of the output function itself. So we perform the linear approximation of our activations before the A becomes an argument to the sigmoid function. And similarly to what we did in case of the regression, we have the approximation is that we have a known point of the activation A at the we have an input vector x, and then we have the fixed vector of weights at the WMAP. And then we have our nearby of this WMAP, we have some weights W, which are then characterized by the offset of the W from the WMAP, and then this is a dot product with the vector B. And the vector B, in this case, is a gradient of the A with respect to the W, so not of the output, but of the activation before it becomes a function of the sigmoid. And this gradient is then evaluated at the value W equals WMAP. So this is the vector B, and B transpose is then forming this dot product with the offset of the weights from the WMAP. And we can find the B by the back propagation by simply performing this active by the process during the process of back propagation. We will be finding these gradients, and we can use it then for our purpose in this approximation. Now we have performed an approximation of the this activation, how it behaves near the WMAP given an input vector x, and now we can also state. So now we will be calculating the predictive distribution of A, and instead of the predictive distribution of the Y, based on our linear approximation. And now we will use for our conditional probability an actual formulation where we have like a Dirac delta, which means that if we have the W known, the probability is actually 1 at the A equals A equals A XW, and everywhere else it is 0. So we have this just infinite spike of the probability at one point, and then for the rest the probability is 0. And we will use this probability distribution here for our conditional probability given the weight W is known, and that therefore we have here this Dirac delta function. And then for the Dirac delta, we are putting into our A our linearly interpolated A x of W, where we have here the AX at WMAP and minus this offset multiplied with our or dot product with our vector. And that is this integral is therefore simply just like a normal distribution with altered the mean, and that's why this integral is again a normal distribution of an A, and similarly to the previous case, as we had discussed in the regression, we have the mean, which is the AX WMAP, as we had previously for Y, but now it's for A, and we have our variance, which is equal to the B transpose A inverse B, because we do not have here this beta inverse as we had in the case of regression. And we need to note, of course, that this all is dependent on the input vector x, as it is here. So this is our predictive distribution for the activation. And then once we have the predictive distribution of the activation, we can use it for defining the predictive distribution of the actual output of the sigmoid. So let's do that in the next. And here simply the predictive distribution of our activation is multiplied with the sigmoid of this activation, and the integral is our predictive distribution of the t, so the x belonging to the class 1, given the new input point x and the training set. So here we need to marginalize over A, and we cannot really solve easily this integral, but we will use this trick with the probit function, which we had in the classification chapter before, where we replace the probit instead of the sigmoid, and then we can actually perform this this integral. And once we solve this integral, because this is normal distribution, once we solve this integral, then the result is actually we again replace the probit with the sigmoid with this slight correction of this term kappa, where the argument is the variance, and multiplied by the activation. So, and this term now is equal to the sigmoid of the activation at the WMAP, and activation at the WMAP, and times this this approximation of a particular probit function to a sigmoid, where we have this 1 plus pi sigma squared divided by 8 powered by minus 1/2. And that is the outcome of our predictive distribution, which is a sigmoid function with this argument with the argument which is containing the activation function. As the final slide, let's have an example of this two-class classification task for our input points, where we have classified them as red axes or blue circles. And we have a 2-layer 8 hidden units network with 10H activation function and with sigmoid activation function in the output layer. And we are showing in this image here how the decision boundaries look like. So you can see the green in some sense characterizing the ideal decision boundary based on the underlying knowledge of the underlying synthetic data set. And although we can see that there is a certain overlap, which is not possible to really resolve in this case. And then we have the decision boundary. So the green is the ideal. Then we have MLE, which is in black, and we can see how this black is overfitting to our distribution of our points, and it's a very complex function here defining this decision boundary. And then we have the result of our regularization with alpha determined with the evidence framework. So we basically calculated the maximum a posteriori distribution, and we can see it here in the red color. So here in the red color, this is after the regularization, where we can see that the decision boundary is much smoother. In the middle and on the right hand side, we can see the classification, but for slightly different values of y. Of course, the value of y being equal to 0.5 is the decision boundary, but we want to see how this y is behaving. What is its shape at the y equals at 0.1, 0.3, 0.7, 0.5, 0.7, and 0.9. And this kind of a change of the y through this contour plot can be seen as a result of this classification training. First, on the predictive distribution approximated by this point estimate with the WMAP. So we can see here exactly this green line here should be in fact exactly the same as the red line here, which it seems to be the case. And then we see how the changes, the y changes away from this decision boundary. And in the right hand side, we see a similar case, however, with the case of the actual sigmoid predictive distribution, which we calculated, and where we have this kappa term, which is coming from this probit approximation of the sigmoid, and we have the activation at the WMAP. So, and we can see that these individual contours are here. Again, the WMAP, the 0.5 is exactly in the same location, but the other isolines at 0.1, 0.3, 0.7, and 0.9 are a little bit more broadly distributed than the ones of the fixed point case, which leads to the conclusion that this more thorough Bayesian treatment is encoding this uncertainty about the associated with the classification in this distribution. And at this point, this is the end of the chapter 5 of the neural networks of the pattern recognition and machine learning book. And we will be continuing with the chapter 6 on kernel methods.